Solutions Chapter 1 Unit 1 of Chemistry Class 12. Unit 1 Solutions. Objectives of this lesson. After studying this unit, we will be able to describe the formation of different types of solutions, express concentration of solution in different units, state and explain Henry's law and Raoult's law, distinguish between ideal and non-ideal solutions, explain deviations of real solution from Raoult's law, describe colligative properties of solutions and correlate these with molar masses of the solute, explain the abnormal colligative properties exhibited by some solutes in solutions. Solutions. Okay, this is chemistry chapter 1 solution speed run, so I'll be doing it. I'll be reading somewhat fast. Almost all processes in body occur in some kind of liquid solutions. Okay, in normal life we rarely come across pure substances like elemental substances, like in elemental forms. Most of these are mixtures containing two or more pure substances. Their utility or importance in life depends on their composition. For example, the properties of brass, which is a mixture of copper and zinc, are quite different from those of German silver, mixture of copper, zinc and nickel. Brass is a mixture of zinc and copper, whereas German silver is a mixture of copper, zinc, which are brass elements, and of course and along with nickel, or bronze, mixture of copper and tin, 1 part per million. These compositions actually, the utility or importance in life depends on their composition, which they are made of, what kind of elemental forms they are made of, and how much of the elemental form is present. 1 part per million ppm of fluoride ions in water prevents tooth decay. 1 part per million of fluoride ions in water prevents tooth decay, while 1.5 ppm causes the tooth to become mottled, and high concentration of fluoride ions can be poisonous. For example, sodium fluoride is used in rat poison. Basically, when fluoride ions when we take 1 part, this is a concentration term, ppm is a concentration term, where if in a million parts one part is a fluoride ion, it is good for our teeth, where it will prevent our tooth decay. But if it is 1.5, which is higher than 1, then it will cause the teeth to become mottled, and high concentration of fluoride ions can be poisonous. Just different concentration of the same thing. At one concentration it is good for us, but at a higher concentration it became poisonous. They gave sodium fluoride as a rat poison. Intravenous injections are always dissolved in water containing salts at particular ionic concentration that match with blood plasma concentration, and so on. Intravenous injections meaning injections which are the doctors directly inject into our blood vessels. Those are called intravenous injections. And those are, in case of saline bottles, they have concentration, they are not pure water, they have a specific concentration of sodium chloride in it, and we will read about it as we go on in this chapter. In this unit, we will consider mostly liquid solutions and their formation. This will be followed by studying the properties of the solutions like vapor pressure, and colligative properties. In this chapter, we will only consider liquid solutions and their formation, and we will be studying about property solutions like vapor pressure and colligative properties. We will begin with types of solutions and the various alternatives in which concentration of solute can be expressed in the liquid solution. Solutions are homogeneous mixtures of two or more than two components. Okay, by homogeneous mixture we mean that its composition and properties are uniform throughout the mixture. Okay, generally the component that is present in the largest quantity is known as solvent. Solvent determines the physical state in which solution exists. Basically, there are two components in a solution, solute and solvent, and solvent is what we call, which is the larger quantity, we call it as solvent. And generally a solution is a homogeneous mixture of two or more than two components. Homogeneous mixture meaning uniform mixture. And in this mixture, the larger quantity component, based on quantity, the higher quantity component we call it as a solvent, and the lower quantity component we call it as a solute. And this solvent is the one that determines the state of the solution. As it is excess, it will only determine the state of the solution. One or more components present in the solution other than the solvent are called solutes. In this unit, we shall consider only binary solution, meaning two component solutions. That is, binary meaning consisting of only two components. Here are each component may be solid, liquid or gaseous state, and these are summarized in table 1.1. Let's see the table. Gaseous solutions, the solute may be in gaseous solutions, the solvent is gas. The solute may be gas in case of mixture of oxygen and nitrogen gases, as we see in the atmosphere, and it can be also liquid in gas, chloroform mixed with nitrogen gas. This is an example. And we can see solid in gas as well. This is camphor in nitrogen gas, basically sublimation, where it turns into gas. And liquid solutions, the solvent is liquid. The solute can be gas in case of oxygen or carbon dioxide dissolved in water. In case of liquid solution, ethanol dissolved in water, basically an alcohol which is dissolved in water. And solid plus plus liquid, which we can take it as glucose dissolved in water, or we can take NaCl, salt plus water, sugar plus water, glucose plus water, etc. Solid solutions. The solvent is solid. The solute can be gas, solution of hydrogen, palladium, liquid, amalgam of mercury with sodium, basically basically it is an alloy of mercury, is called amalgam, I think, right? Alloy mercury is called amalgam. Yes, that is correct. Where mercury is one of the components. Okay. And a solid solution is a copper dissolved in gold. Basically this is also a kind of alloy where we take mercury in case of liquid solid solution, because mercury is liquid in room temperature. Okay, basically a gas solution is the atmosphere air, a liquid gas solution is chloroform in air, and solid gas solution is camphor or naphthalene, we can say. Liquid solution is gas, liquid is oxygen or carbon dioxide dissolved in water. Liquid is alcohol dissolved in water. Solid liquid is glucose, sugar, salt dissolved in water. And in case of gas solid, we can take hydrogen in palladium. Liquid solid, we can take amalgam of mercury and sodium. Sodium, we can take copper in gold. Expressing of concentration of solutions. Composition of a solution can be described by expressing its concentration. The latter can be expressed either qualitatively or quantitatively. For example, qualitatively, we can say that solution is dilute. Basically, they are saying that we can describe the concentration of a solution qualitatively or quantitatively. Quantitatively meaning how much exactly is the concentration. Qualitatively meaning is it dilute or concentrated. In case of dilute, qualitatively we can say it is dilute, that is relatively very small quantity of solute compared to the solution. Or if we say it is concentrated, relatively very large quantity of solute. But in real life, these kinds of description can add to lot of confusion, as we cannot say based on a qualitative analysis alone or description alone, we cannot say how much concentrated or how much dilute a solution is. Because of such a reason, it will cause a lot of confusion, and thus there is a need for quantitative description of the solution. There are several ways which we describe the concentration of the solution quantitatively. Mass per mass percentage, where we take weight of the mass of the component in the solution, basically mass of solute. Not WWE. Mass percentage is mass of solute by mass of solution times 100, as we take it as not mass by mass ratio, but is a mass percentage. As such, we take it as mass of solute by mass of solution times 100. The mass percentage of a component of a solution is defined as mass percentage of the component, and mass of the is equal to mass of the component in the solution by total mass of the solution times 100. For example, if a solution is described by 10% glucose in water by mass, described by 10% glucose in water by mass, it means there is 10 gram of glucose dissolved in 90 gram of water, resulting in a 100 gram solution. The total solution, we take it as the 100% mass, and out of which we segregate the masses of solution and solute. In here, when we take 10% of glucose solution, which means in a 100 gram solution 10 grams of glucose is there, in a 1000 gram solution 100 grams of glucose is there. Concentration described by mass percentage is commonly used in industrial chemical applications. For example, commercial bleaching powder solution contains 3.62 mass percentage of sodium hypochlorite in water. 3.62 mass percentage meaning 3.62 grams per 100 grams of water. 3.62 grams of sodium hypochlorite. Volume percentage. The volume percentage is defined as it is similar to the mass percentage, where we take mass of solute by mass of solution. Here volume percentage is volume by volume percentage, VV equals mass of solute by volume of solute by volume of solution. This we can take in case of liquid solutions or gas solutions, where we can take the exact volume, and in this case we can take the volume of the component meaning volume of the solute by total volume of the solution times 100. Basically the same as saying if 10 ml of, if 10% is the concentration, then in a 100 ml solution, 10 ml is whatever we have taken of a solute. Or in case of a 1000 ml solution at 10% concentration, volume by volume concentration is 100 ml. For example, 10% ethanol solution in water means that 10 ml of ethanol is dissolved in water such that the total volume is 100 ml. Basically 90 ml of water is dissolved. Solution containing liquids are commonly expressed in this unit. For example, 35% volume by volume solution of ethylene glycol. Basically, as I said before, this is used in solution containing liquids. For example, a 35% volume by volume solution of ethylene glycol, an antifreeze used in cars for cooling the engine. At this constant concentration, the antifreeze lowers the freezing point of water to 255.4, which is minus 17.6 degree. This is a point to be remembered. This we will study more about in the colligative properties topic, where depression in freezing point due to solute, which is we can take ethylene glycol, where normally the freezing point of water is around 273 Kelvin or 0 degrees Celsius, but due to addition of ethylene glycol, the freezing point got decreased to 17.6 degrees. So due to this, the water won't freeze and the engines will be working. Ethylene glycol, which is two OH groups attached to an ethane molecule. And the third concentration term is mass by volume percentage, W by V, another unit which is commonly used in medicine and pharmacy and is by mass by volume percentage. It is the mass of solute dissolved in 100 ml of solution. And the fourth concentration term is parts per million, which we saw about fluoride ions. If 1 part per million, it is good for us, but when it goes to 1.5, it is danger. It causes teeth damage. When it is 1, it will help the quality reduce tooth decay, but when it exceeds a certain concentration, it is dangerous. Where a solute is present in trace quantities, it is convenient to express in concentration in parts per million, and it is defined as number of parts of the solute by total number of the parts of all the components of the solution. Similar to the before ones, if 10 is the 10 parts per million, 10 ppm, then in a million parts, 10 parts is the solute, and this we multiply by 10 power 6. As in case of a percentage, concentration in parts per million can also be expressed as mass to mass, volume to volume, and mass to volume. A liter of seawater, which weighs 1030 grams, approximately 1000 grams, 1 kg, contains about 6 into 10 power minus 3 gram of dissolved oxygen. Such a small concentration is expressed as 5.8 gram per million grams, 5.8 ppm, parts per million of seawater. The concentration of pollutants in water atmosphere are often expressed in terms of microgram per liter. Microgram per liter, I believe. Yes, basically they are saying this parts per million. We can actually in case of volume, mass, or mass by volume, we can only express them by mass and volume, or volume, or mass and mass in their specific topics or cases. But in parts per million, any substance, we can express in case of mass, volume, or volume mass. That is what they're saying here. And there is also parts per billion, even where it is even smaller molecules or smaller quantities of molecules. And there is one more concentration term, it is mole fraction. Commonly used symbol for mole fraction is chi, and subscript used on the right hand side of the chi denotes the component. Basically This is the symbol for mole fraction, and this is the subscript. If chi A, then it means that it is a this chi mole fraction is a part. If Let's continue. It is defined as mole fraction equals number of moles of the component by total number of moles of the components. Basically, number of moles of solute by total number of all the moles. For example, in a binary mixture, if the number of moles of A and B are Na and Nb respectively, the mole fraction of A will be chi A equals Na by N plus Nb. For a solution, Na plus Nb. For a solution containing I number of components, we have chi A equals N1 by N1 plus N2 plus and so on till Ni, which we can represent as N1 by sigma Ni, summation Ni. It can be shown that in a given solution, sum of all the mole fraction in unity is equal to 1. All the mole fractions, if we add, it will be equal to 1, because they are all fractions of the molecules. In case of, for example, in a binary solution of A plus B, chi A, basically this is what they meant by subscript component. The component is mentioned in the subscript. In case of mole fraction of A, we are doing number of moles of A by number of moles of B plus number of moles of A. In case of chi B, we have Nb by Na plus Nb. If we both add them, plus chi A plus chi B, it is Na plus Nb. Both have same denominator of Na plus Nb. So this will be equal to 1. That is what they said here. Okay. Mole fraction unit is very useful in writing some physical properties of solutions, say vapor pressure with the concentration of solution, and quite useful in describing the calculations involving gas mixture. We can describe many physical properties due to this mole fraction. We can this is vapor pressure. We can say the pressure due to the vapor is what we call as vapor pressure. I will not be calculating the questions here. I will just be reading through. Calculate the mole fraction of ethylene glycol C2H6O2 in a solution containing 20% C2H6O2 by mass. Okay, as by mass meaning, okay, assume that we have 100 grams of solution. One can start with any amount of solution because the results obtained will be same. Solution will contain 20 gram of ethylene glycol and 80 gram of water. Molar mass of C2H6O2 is 62 gram per mole, and moles of C2H6O2 is 0.322 mole. Okay, moles of water is 80 gram by 18 gram, which is the molar mass of, molecular mass of water is 18 gram, which is equal to, which we divide, we will get 4.444 moles. Then glycol mole fraction, if we find, it will be approximately 0.068, and mole fraction of water, if we calculate, it will be 0.932. One more way of calculating is, as we know, chi A plus chi B will be equal to 1. We know chi A, so 1 minus chi A equals chi B. That is what they used here. We will get the same answer, approximately the same answer. The next concentration term is molarity. Molarity, capital M, is denoted by capital M, is defined as number of moles of solute dissolved in 1 liter of solution. Molarity, moles of solute by volume of solution in liter. Till here we saw that the denominator, we are considering the whole solution and not the solvent. But in the next concentration term, which is molality, MOLALITY. We are going to see that. For now, let's see molarity itself. Moles of solute by volume of solution in liter is called what we call molarity. For example, 0.25 molar solution, mole per liter. Mole per liter is a unit for molarity. We can call it as either mole per liter or molar. Solution of NaOH means that 0.25 mole of NaOH has been dissolved in 1 liter of water, or we can say 1 liter equal to 1 cubic dm cube, basically dm cube, 1 cubic decimeter. Okay, calculate the molarity of solution containing 5 gram of NaOH in 450 ml. Divide, first find the moles of NaOH, which is around 0.125, then number of moles per the liter, the number of amount of liters of the solution, which is around 450 ml. If we divide this 450 by 1000, the 1000 will go up. We will get a molarity of 0.278 molar. This we can write it as mole per liter, molar, or mole per decimeter cube. Then, as I said before, the next term is molality. Molality, represented by molal or small m, is defined as the number of moles of the solute per kilogram of the solvent. As I said before, molality, which is different from all the other concentration terms we saw in as far as I have done till now. This molality, we consider moles of solute by mass of the solvent in kg. Solvent and not the solution. Molarity, we consider only the solvent. Basically, it is the number of moles of solute dissolved in 1 kg of solvent. For example, 1 mole per kg or 1 molar solution of KCl means that 1 mole 74.5 grams of KCl is dissolved in 1 kg of water. Each method of expressing concentration of the solutions has its own merits and demerits. Mass percentage, parts per million, mole fraction, and molality are independent of temperature, whereas molarity is a function of temperature. This is because volume depends on the temperature but mass does not. In case of molarity, there is no volume. Volume depends on temperature but mass doesn't. In case of molarity, there is no volume, so independent of temperature. But in case of molarity, it is mass per liter. Liter is volume and volume depends on temperature. In case of other concentration terms of mole fraction, it depends on the amount of substance, so it doesn't depend on volume, so it also doesn't depend on temperature. In case of parts per million, it only depends on the parts or amount of the component or number of the component, so it doesn't depend on volume. Mass by volume percentage, this does depend on volume. Here we see it as volume, so mass by volume percentage is dependent on temperature. Volume by volume is also dependent on temperature, but mass by mass is not dependent on temperature. So mass by volume, volume by volume, and molarity depend on temperature, whereas others don't. I will not be doing the questions. Calculate the mass percentage of benzene and carbon tetrachloride if 22 grams of benzene is dissolved in 122 grams of carbon tetrachloride. Okay, this is basically mass percentage. Mass percentage is the mole fraction, not mole fraction, the number of moles, not moles actually. It is the weight of the solute by weight of the solution. Basically calculate the mass percentage. And carbon tetrachloride. Benzene is taken in the little amount and carbon tetrachloride CaCl4 is taken in the large amount. So basically the answer will be, I am actually calculating. So 22 benzene and carbon tetrachloride. If is 22 plus 122, so it is 22 by 144 times 100 times 100, we will get the answer. Calculate the mole fraction of benzene in solution containing 30% biomass in carbon tetrachloride. They say it is 30 mole fraction of benzene. If benzene is 30% biomass in carbon tetrachloride solution, they are saying 30 is the value for mass of benzene by mass of solution times 100. So 30 by 100 equals mass of benzene by mass of solution. Okay, if mass of solution is around 100 grams, then mass of benzene is 30 grams. Then we find the number of moles of benzene when we take mass of solution to be 100 and mass of benzene to be 30 grams. 30 by molecular mass of benzene by 30 by C6H6 benzene plus 70 by carbon tetrachloride CCl4, the molecular mass of CCl4. That is how you solve this question. Okay, the third question, calculate the molarity of each of the following solutions. 30 grams of CONO3 twice 6H2O in 4.3 liter of solution. Basically molarity, so they gave the formula here, they gave the mass of the CONO3 twice, basically cobalt nitride, I think cobalt nitride, and 6H2O in 4.3 liter solution. We should calculate cobalt nitride and 6H2O, and we calculate the number of moles, and then we divide it by the mass of the the volume of the solution, which is around 4.3 liter. Now 30, the second one molarity is 30 ml of 0.5 molar H2SO4 diluted to 500 ml. Okay, this is the dilution law. Basically M1 V1 equals M2 V2. I think this is the dilution law. Yes, M1 V1 equals M2 V2, where M1 is the molarity of the first solution, where they gave it as 0.5, and 30 ml is the volume. Then we need to find M2, and V2 is 500 ml. So substitute is in this equation, we will get the answer. Next, calculate the mass of urea required in making 2.5 kg of 0.25 molar aqueous solution. They gave the mass of solution to be how much? 2.5 kg. 2.5 kg is the mass of the solution, and they gave molality 0.25 molality. Basically substitute in the formula, we will get the mass of the number of moles of urea. Then we calculate, we know that given mass by molecular mass equals to number of moles. When we get number of moles times the molecular mass, we will get the given or taken weight. This is how we solve this question. Calculate A molarity, B molarity, and mole fraction of potassium iodide if the density of 20% mass by mass aqueous Ki is 1.202 gram mole per liter. There is a specific formula for this, and based on that formula, using density, we will get the answer. I do not remember the formula, so I will not be giving it to you. Solubility. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature. It depends upon the nature of solute and solvent as well as the temperature and pressure. Okay, solubility of a substance is its maximum amount that can be dissolved in a specific amount of solvent at a specified temperature. Okay, it depends upon the nature of solute, solvent as well as the temperature and pressure. Depends on nature of solute, nature of solvent, amount, the temperature and the amount of pressure. Let us consider the effect of these factors in the solution of a solid or a gas in a liquid. Let us consider the effect of these factors in solution of a solid or a liquid. Okay, fine. How does this affect in the solution of solid or a gas in a liquid? Solubility of a solid in a liquid. Every solid does not dissolve in a given liquid. While sodium chloride and sugar dissolve readily in water, naphthalene, anthracene do not dissolve in water. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar do not. It is observed that polar solutes dissolve polar solvents and non-polar solutes in non-polar solvent. Basically, they are saying like dissolves like, unlike dissolves unlike. It's actually like dissolves like only, so polar it will dissolve, non-polar it will dissolve. Non-polar solutes in non-polar solvents, polar solutes in polar solvents. In general, a solute dissolves in a solvent if the intermolecular interactions are similar in the two, or we may say like dissolves like. Basically, they are saying a solute dissolves in a solvent if the intermolecular interactions are similar in the two, in the solute and solvent. When a solid solute is added to the solvent, some solute dissolves and its concentration increases in the solution. This process is known as dissolution. Some solute particles in the solution collide with the solid solute particles and get separated out of the solution. Some solute particles in solution collide with the solid solute particles and get separated out of the solution. This process is known as crystallization. A stage is reached when two processes occur at same rate. Under such conditions, the number of solute particles going into solution will be equal to the solute particles separating out, and a state of dynamic equilibrium is acquired or reached. Solute plus solvent, it will change into, basically they are saying a stage is reached when two processes occur at the same rate. The process is known as dissolution. Some solute particles in the solution collide with the solid solute particles and get separated out of the solution. This process is known as crystallization. Two processes occur at the same rate, and under such conditions, the number of solute particles going into the solution will be equal to the solute particles separating out. Okay, when we dissolve anything like sodium chloride or such in the solution, there is a dynamic equilibrium state where solute and solvent exist separately on the left hand side here, and they mix to give the solution in the right hand side. This state is the dynamic equilibrium, and when under this dynamic equilibrium, the number of solute particles going into the solution, meaning dissolving into the solution, dissolution into the solution, will be equal to the solute particles which will come out of the solution. They will not come out of the beaker or the solution actually, but they will come out of the dissolved state, and this other state which is not the dissolved form is what we call a crystallized state or a crystallization. That is basically what they described here. And this stage, and this happens due to the collision of the separated out the non-dissolved particles with the dissolved particles. This will bring out dissolved particles, and this will also bring particles to get dissolved. At this stage of dynamic equilibrium, the concentration of solute in the solution will remain constant under the given conditions, that is temperature and pressure. When same amount of solutes are getting dissolved and same amount of solutes are getting crystallized, then the concentration in the solution or of the solution will remain constant. That is under temperature, under constant temperature or given temperature and pressure. Similar process is followed when gases are dissolved in liquid solvents. Such a solution in which no more solute can be dissolved at the same temperature and pressure is called a saturated solution. An unsaturated solution in one which more solute can be dissolved at the same temperature. The solution which is in dynamic equilibrium with undissolved solute is a saturated solution and contains the maximum amount of solute dissolved in a given amount of solvent. Solution which is in dynamic equilibrium with undissolved solute is the saturated solution and contains, basically they defined saturated, unsaturated solutions. Saturated solutions are solutions at given temperature and pressure. They cannot dissolve more solute. And unsaturated, they can dissolve more solute. The solution which is in dynamic equilibrium, basically this is the dynamic equilibrium state with undissolved solute, is the saturated solution and contains the maximum amount of solute given amount of solvent. Thus, the concentration of a solute in such a solution is its solubility. The concentration of solute in such a solution is its solubility. This is the property of the solute. Earlier, we have observed that solubility of one substance into another depends on the nature of the substances. In addition, these variables, two other parameters of temperature and pressure, also control this phenomenon. Now, how they control is effects of temperature. The solubility of solid in a liquid is significantly affected by temperature changes. How so? Consider the equilibrium represented by equation 1.10. This equation. This being dynamic equilibrium must follow Le-Chatelier's principle. In general, if a nearly saturated solution, let's see what Le-Chatelier's principle is. What is Le-Chatelier's principle? Okay. Le-Chatelier's principle is a fundamental concept in chemistry that describes how a system at equilibrium responds to disturbances. Le-Chatelier's principle's definition: when a system at equilibrium is disturbed by a change in concentration, temperature, pressure, or volume, the system shifts its equilibrium position to counteract the disturbances and restore a new equilibrium. Types of disturbances and system responses: change in reaction, adding a reactant shifts equilibrium to right towards the product. Removing a reactant, shift towards the left towards the reactant. Change in pressure for gases, only increasing pressure, shift towards the side with fewer moles of gas. Decreasing pressure, shift towards the side with more moles of gas. Decreasing pressure, it will shift toward the side with more moles of gas. more moles of gas. Change in temperature for exothermic reaction, heat is a product. Increase in temperature for exothermic reactions, as they will release heat, where as we increase the temperature it will shift towards the left. As for decrease in temperature, it shifts towards the right. For endothermic reaction, heat is the reactant, so increase in temperature, product is formed. Decrease in temperature, it will go back to the left, reactant is formed. Addition of a catalyst, no effect on equilibrium position, but it speeds up the attainment of equilibrium. Basically, this is like the law of inertia, where the particle in motion or in rest will continue to stay like that. It is not exactly similar, but I can relate it to the law of Newton's law of inertia, where here as well the system, when we change its state or we disturb its equilibrium, it will still try to retain its equilibrium by changing the side or reaction side, like forward or backward reaction. Or this change in concentration, how Le-Chatelier's principle works is, in case of adding a reactant, it will go towards the product side. When we increase the concentration of reactant, more reactant will be there, so we go towards the product side. When we remove a reactant, we are reducing the concentration of the reactant, then product concentration will be more, so more product, so the reaction will go backward, which means products will produce reactants. When in change in pressure, increasing the pressure, when there is high pressure, the reaction will be towards the gases with lesser moles, lesser amount of substance. But when we decrease the pressure, the more moles of substance will react to give the product. And as for temperature, exothermic, when we increase the temperature, we do not need to increase, so it will be reactant side, it will shift toward the reactant side. When we decrease the temperature, it will shift toward the product side. Because it's an exothermic reaction, it doesn't need temperature. Because of that, it is more for the forward reaction, decrease in temperature is more favorable. For endothermic reactions, heat is reactant, meaning heat is required because it needs energy. In such a reaction, for the forward reaction, high temperature is favorable. For when we decrease the temperature, it will shift towards the backward reaction. Catalyst doesn't affect the no effect on the equilibrium position. A catalyst has no effect on equilibrium position, but this speeds up the attainment of equilibrium, basically speeds up the reaction. This is the Le-Chatelier's principle, where when we disturb the equilibrium of a system, it will try to retain its equilibrium. The system shifts its equilibrium position to counteract the disturbances and restore a new equilibrium. Effect of temperature. Let's start reading from again. The solubility of a solid in liquid is significantly affected by temperature changes. Consider the equilibrium represented by equation 1.1, solute plus solvent, one state, forward and backward, solution. Okay, this is the equation 1.1. This being dynamic equilibrium must follow Le-Chatelier's principle. In general, if in a nearly saturated solution, the dissolution process is endothermic, meaning it will need energy. For the solute to dissolve in water, maybe due to bond breaking, it needs energy, where the enthalpy of dissolution is more than zero, it requires energy. The solubility should increase with the rise in temperature, as we saw before. For endothermic reaction, when for dissolution it is endothermic, then we need to provide energy. And in the case of it is exothermic, it when it dissolves in water, it will only release energy. In such a case, H should be lower than 0. It is releasing energy, loss of energy. Then the solubility should increase with decrease in temperature. These trends are also observed experimentally. Then effect of pressure. Pressure does not have any significant effect on solubility of solids in liquids. It is so because solids and liquids are highly incompressible and practically remain unaffected by changes in pressure. But it does affect gases in liquid, as we will see the law of Henry's law. Solubility of a gas in a liquid. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. Okay. It is dissolved. It is this dissolved oxygen which sustain all aquatic life. On the other hand, hydrogen chloride gas is highly soluble in water. Solubility of gases in liquids is greatly affected by the pressure and temperature. Gases in liquid is affected by both temperature and pressure. Solubility of gases increases with increase in pressure. Higher the pressure, higher the solubility of solution. K is solubility is directly proportional to pressure. Solubility directly proportional to pressure. For a solution of gases in a solvent, solution of gases in a solvent. Consider a system as shown in figure 1.1a. 1.1a, effect of pressure on solubility of a gas. The concentration of dissolved gas is proportional to the pressure on the gas above the solution. Effect of pressure on the solubility of gas. Okay, this is a piston, this is a solution, this is at low pressure or at some pressure due to this weight. Here in this case, when at low pressure the dissolution is less dissolution, less solubility. But in this case where the pressure is high, solubility is also high. This is the partial pressure of HCl. This is the mole fraction. We describe solubility of gases in terms of mole fraction. This is a mole fraction of HCl in its solution in cyclohexane. As we increase the pressure, higher the mole fraction. It is a completely linear graph. It increases, it is directly proportional. The lower part is the solution and the upper part is this is the solution, this is the gas. At the pressure P and temperature T, assume the system to be in a state of dynamic equilibrium. That is, under this condition, rate of gaseous particle entering and leaving the solution phase is the same. Now increase the pressure over the solution phase by compressing this gas to smaller volume. This will increase the number of gaseous particles per unit volume of the solution and also the rate at which the gaseous particles are striking the surface of the solution to enter it. The solubility of the gas will increase until a new equilibrium is reached, resulting in an increase in the pressure of gas above the solution, and thus its solubility increases. Henry was the first to give a quantitative relation between pressure and solubility of gas in a solvent, which is known as the Henry's law. The law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. Dalton, this is the law. Basically, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution. Dalton, a contemporary of Henry, also concluded independently that the solubility of a gas in a liquid solution is a function of partial pressure of gas. Basically saying solubility of gas in a liquid depends on the partial pressure of the gas. If we use a mole fraction of a gas in the solution as a measure of its solubility, as I said before, solubility in gases is measured by or through mole fraction and not in via concentration terms, then it can be said that the mole fraction of gas in the solution is proportional to the partial pressure of gas over the solution. Most commonly used form of Henry's law states that the partial pressure of gas in a vapor phase is proportional to the mole fraction of the gas in the solution and is expressed as P equals KH and chi, where P is the partial pressure of the gas in vapor phase and basically gaseous phase, KH is the Henry's constant, chi is the mole fraction, not molar fraction, it is mole fraction. Here KH is the Henry's law constant. If we draw graph between the partial pressure of the gas versus mole fraction of the gas in a solution, then we should get a plot of the type shown in figure 1.2, a linear graph. Different gases have different KH values at the same temperature. This suggests that KH is a function of the nature of the gas. Meaning, they are basically saying because different gases have a different KH values, Henry's constant, they suggest that KH depends on the nature of the gas. Basically depends on different gases. This graph is the experimental result of the solubility of HCl in cyclohexane C6H12 at 293 Kelvin. The slope of the line of the Henry's law constant. The slope of the line is the Henry's law constant KH. Partial pressure, basically they are saying that P equals KH, then K equals partial pressure by, this is not H actually, then KH equals partial pressure by mole fraction. That is why when we take the slope of the graph of partial pressure to mole fraction, we will get the slope to be Henry's constant. This will be different for different gases. It is obvious from the equation 1.11 P equals KHX that higher the value of KH at a given temperature or pressure, at a given pressure, the lower its solubility of the gas in the liquid. If we see here, KH is inversely proportional to mole fraction. As KH increases, mole fraction decreases. That this is through this formula. KH equals P by chi. As mole fraction increases, chi decreases. As chi increases or mole fraction increases, Henry's constant is low for that gas. Lower is its solubility. It can be seen from table 1.2 that KH values for both N2 and O2 increase with that of temperature, indicating that the solubility of these gases increases with decrease in temperature. It is due to this reason that aquatic species are more comfortable in cold waters rather than in warm waters. Basically, they are saying that the KH values of oxygen and nitrogen are high, very high, and because of such a reason, its dissolution in water is also low. and here we see helium has the highest dissolution value. This is in water, value of Henry's law constant kH for some selected gases in water. In case of helium, kH by K bar, this is 144.97, which is the highest we see here in this table. Helium having the least solubility. The highest solubility we see is in formaldehyde, HCHO, which is having the least and is the most soluble in water according to this table. And H2 is somewhat soluble, and N2 has a relatively higher compared to higher KH value and lower solubility compared to H2. And in case of oxygen, in case of nitrogen, in higher temperature, a total of 10 degree higher temperature, the KH value increased even further, which means its solubility basically decreased. The same can be seen in oxygen, even though the dissolution of oxygen is very less compared to nitrogen, it is still somewhat there. As temperature increases for oxygen and nitrogen, the dissolution decreases. Because of such a reason, at cold waters, aquatic life which depend on the oxygen that dissolve in water, oxygen dissolve easily in cold water, so the aquatic life are more comfortable in cold water itself. Argon is also very insoluble in water, but which is similar to oxygen comparatively. In case of CO2, it has a relatively low KH value, so it can easily dissolve in water. Formaldehyde, the least KH value, the most solubility. Methane also, it's in the points, 0.413. It's also dissolvable in water. Vinyl chloride, it's also dissolvable in water. Let's see the example. If N2 gas is bubbled through water at 293 Kelvin, how many millimoles of N2 gas would dissolve in 1 liter of water? Assume that N2 exerts a pressure of 0.987 bar, given that Henry's law constant for N2 at 293 Kelvin is 76.48. Basically, they are asking us to use the formula P equals KH chi. They are asking if you pass N2 gas over water or into water, how many would it dissolve? They gave the value of the KH. For KH they gave the value. Pressure they gave the value, which is around close to 1 bar. And they gave and basically they are asking what is solubility, the number of moles of nitrogen. We can take the total moles to be a constant, or the total moles to be 1 in 1 liter of water. 1 liter by 18. 1 liter if we convert into moles for water, which is around 22.4 moles, I think. How many moles for 1 liter of water? It's okay. It's around 55.5 moles, not 24. But in STP, should the number of moles in 1 liter of anything be 22.5 4. No, okay. Basically, it is not, okay, I was confused. It is 1 mole of ideal gas occupies 22.4 liters. Ideal, it's only for gases. A gas, 1 mole of gas occupies 22.4 liters and not 22.4 moles. And 1 liter of water has 1000 grams, and 1000 grams approximately if we take, which is 55.4 mole, I mean 55.5 mole. Okay. Yes, so the same thing they are doing here. The solubility of nitrogen they found out to be 1.29 into 10 power minus 5, which is what we saw. Right. As 1 liter of water contains 55 mole of it, as we found out here. Therefore, if N represents number of moles of N2 in solution, then N mole plus 55 mole, then you will get approximate value is 1.29 into 10 power minus 5, and N is the denominator. Okay, basically they are saying that they neglected N because it is a very, very small value, and we will get, because of neglecting the N mole in the denominator, we will get N by 55.5, which is equal to the solubility here, or the mole fraction. Then when we get the N value, it should be 0.76 into 10 power minus 3 mole, or 0.76 millimole. Henry's laws find several applications in industry and explain some biological phenomena. Notable among these are increase the solubility of CO2 in soft drinks and soda water. The bottle is sealed under high pressure. Basically, carbon dioxide is dissolved in soft drinks and soda water under high pressure. Because of this increases the solubility of CO2 in water. Because of the high pressure, we saw that partial pressure is directly proportional to solubility. So at high pressure, carbon dioxide, which is somewhat which has a 1.46 or something KH value, will dissolve 1.67 at 298 Kelvin, will dissolve more easily in water. And the second biological phenomena explained is, or used in, is scuba divers must cope with high concentration of dissolved gases while breathing air at high pressure underwater. Increased pressure increases solubility of atmospheric gases in blood. When the divers come towards the surface, the pressure gradually decreases. This releases dissolved gases and leads to the formation of bubbles of nitrogen in the blood. This blocks capillaries and creates a medical condition known as bends, which are painful and dangerous to life. Basically, under high concentration, various gases dissolve in the blood, and this blood, as we go up, they return to their solute stage, which are gases. In the blood veins, if we see gas molecules, this will form bubbles in the blood veins. This is a condition known as bends. It is very painful, very, very painful, and it is also very dangerous to life. It could also be fatal if not treated. To avoid bends, as well as the toxic effect of high concentration of nitrogen in blood, the tanks used by scuba divers are filled with diluted with helium, 11.7 helium, 56.2% nitrogen, and 32.1% oxygen. Basically, by reducing the percentage of nitrogen, we are reducing the partial pressure of nitrogen in the air tank. As solubility depends on the partial pressure, when the partial pressure of nitrogen decreases, the solubility also decreases. And the third is, at high altitudes, the partial pressure of oxygen is less than that at the ground level. This leads to low concentration in the blood and tissues of people living at high altitudes and climbers. Basically, at high altitudes, the partial pressure of oxygen is less than that at the ground level. Okay, this leads to low concentration of oxygen in the blood and tissues of people living at high altitudes of or climbers. Okay, low blood oxygen causes climbers to become weak and unable to think clearly. Symptoms of condition are known as anoxia. Because of the low blood oxygen, the climbers can't think clearly. Effect of temperature. Solubility of gases in liquids decrease with rise in temperature. Solubility of gases in liquids decreases with rise in temperature. Okay. When dissolved, the gas molecules are present in liquid phase, and therefore the process of dissolution can be similar to condensation, and heat is evolved during this process. Because we are considering when gas is dissolved in water, we are considering it to be an exothermic process because heat is released. In an exothermic process, according to Chartier's principle, the forward reaction, the dissolution process, is more preferred at lower temperature. So as we increase the temperature, the dissolution process is decreasing. So we say it is inversely proportional. Temperature is inversely proportional to solubility in case of gas dissolving in liquids. We have learned in the last section that dissolution process involves dynamic equilibrium and must follow Lee-Chartier's principle. As dissolution is an exothermic process, the solubility should decrease with increase in temperature. In text question, H2 gas, H2S, a toxic gas with a rotten egg-like smell, is used for qualitative analysis. Okay, if the solubility of H2S in water is at STP is 0.195 molal, calculate Henry's law constant. Okay, they gave molality, they are asking to find Henry's law constant. They gave molality, no wait. So they gave is, I think that is number of moles. No. If the solubility of H2S in water at STPs, let's see. Yes, Henry's law formula, where solution so mole fraction is equal to, wait, Henry's law is P equals KH mole fraction, and another form is solubility equals KH times partial pressure. This is indeed molal pressure at 1 atm because it's STP, and when we substitute in the formula, you will get concentration by pressure, which is equal to the KH value. But I have a confusion. They gave the formula is solubility equals KH times partial pressure, but I saw the formula in the textbook. It is partial pressure equals KH times solubility. Isn't the Henry's law formula, partial pressure equals Henry's product of Henry's constant and mole fraction. There are two common forms of Henry's law depending on the context. Mole fraction form, P equals kH times mole fraction. Partial pressure of the gas in ATM. Mole fraction of gas in solution. Henry's law constant in ATM. Concentration form. Basically, this is the pressure form they are saying. And then there is the concentration form of the gas, which is C equals this has a different unit, mole per liter per ATM, but here Henry's law constant, it is in ATM. This is used, the solubility is given as molarity or molality. In this case we get it as mole fraction, because mole fraction is unitless. The pressure and Henry's law have the same constant, the same value or the same unit, but here pressure has a different unit, and because of such a reason I know that the KH values are changing, but just in case. They are going to differ. Fine. This question is the second form. The first form of Henry's law is pressure equals KH times and mole fraction, and the second form is concentration equals KH times pressure. This mole fraction constant, Henry's constant, partial pressure. Concentration in molarity terms, this is partial pressure. Okay, these are the two forms. The above are the two forms of Henry's law. Okay, next. Then let's see. The Henry's law constant for CO2 in water is 1.67 into 10 power 8 Pascal at 298 Kelvin. Calculate the quantity of CO2 in 500 ml of soda water when packed under 2.5 atm CO2 pressure. Basically just use the formula, we will get the answer. But for conversion between atm and pascal, 1 atm equals 1.01 into 10 power 5 pascal. This is a conversion. So 1.67 into 10 power 8 pascal at 298 Kelvin. Then the when we convert into atm, the pressure should be around 167 atmosphere. Yes, no, it is 1670 atmosphere actually. It's 1670 atmosphere at 298 Kelvin. The quantity of CO2 in 500 ml of soda water, then packed under 2.5 atm of pressure at 298 Kelvin. atm to pascal conversion. Yes, as I said before, it is 1.01 into 10 power 5. And I got confused by the saying the values. I multiplied it. So we should actually divide this by into 10 power 3. So it will be 1.67 into 10 power 5 atm. Using the P equals kH times mole fraction, we will get the answer. Vapor pressure of liquid solutions. Liquid solutions are found when solvent is a liquid. The solute can be a gas, a liquid, or a solid. Okay. Solutions of gases in liquids have already been discussed in section 1.3.2. In this section, we shall discuss the solutions of liquids and solids in a liquid. Such solution may contain one or more volatile compounds. Generally, the liquid solvent is volatile. The solute may or may not be volatile. We shall discuss the properties of only binary solution, that is solutions containing two components, namely the solutions of liquids in liquids and solids in liquids. Vapor pressure of liquid solution. Let us consider a binary solution of two volatile liquids and denote the two components as 1 and 2. When taken in a closed vessel, both the components would evaporate and eventually an equilibrium would be established between vapor phase and the liquid phase. Let the total vapor pressure at this stage be P total and P1 and P2 be the partial vapor pressure of the two components. Okay, 1 and 2 respectively, these partial pressures are related to the mole fractions chi1 and chi2 of the two components 1 and 2 respectively. We are taking the vapor pressures of the solution as chi1 and chi2. Okay, let's read the statement again. Let us consider a binary solution of two volatile solutions and denote two components as 1 and 2. When we take in a closed vessel, both the components would evaporate and eventually an equilibrium would establish between vapor and liquid phases. Let the total vapor pressure at this stage be P total and P1 and P2 be the partial pressures of the two components of 1 and 2. Okay, these mole, okay, we are not denoting partial pressures as mole fractions. Mole fractions is the amount of substance in the solution, amount of solution 1 in the whole solution and amount of solution or component 2 in the whole solution. That is the mole fraction. So basically they are saying the partial pressures shown by the each of the components is related to the mole fractions of each of the components. That is the statement. The French chemist Francois Marc Raoult 1886 gave the quantitative relationship between them. The relationship is known as the Raoult's law, which states that for a solution of volatile liquids, okay, the partial pressure or vapor pressure of each component of the solution is directly proportional to its mole fraction in the solution. Thus the component, basically they said partial pressure of 1 is directly proportional to the mole fraction of 1. To introduce a proportionality constant, we used P01. P01 is the vapor pressure of the component when it is in a singular solution, when it is the only solution there. It is not in a solution, but it is actually the only one present. There is a P pure pressure, where P0 is the vapor pressure of the pure component 1 at the same temperature. Similarly for component 2, P2 equals P2 chi2, where P2 represents the vapor pressure of the pure component 2. According to Dalton's law of partial pressures, the total pressure P total over the solution phase in the container will be the sum of the partial pressures of the component of the solution, given as P total equals P1 plus P2. Substituting the values of P1 and P2, we get P total equals chi1 P0 1 plus chi2 P0 2, and when we know that in a binary solution chi1 plus chi2 we know that in a binary solution chi1 plus chi2 equals 1. So even if we don't know the chi2 value or chi1 value, we can get it easily for a binary solution. Chi2, if we don't know, we can substitute chi2 value as 1 minus chi1. This is what they did here. Following conclusions can be drawn from equation 1.16. Total vapor pressure of the solution can be related to the mole fraction of any one of the component, because we are using only one of the components here. Wait. Okay. In this case, they just spread out the formula basically. Raoult's law. Raoult's law is P total, no wait, partial pressure of 1 depends on the mole fraction of 1. Partial pressure is equal to the where P pure 1 times the mole fraction. This P0 is a pure vapor pressure, and it is acting as a proportionality constant, and so P total equals, in a binary solution, P1 plus P2. In such a case, P total equals P1 plus P2, where P1 is P01 chi1 plus P0b chi2. I mean not P0b, it is P02 chi2. In this, where we know that in a binary solution chi1 plus chi2 equals 1. So if we do not know the chi2 value, chi1 chi2 equals 1 minus chi1. This, if we substitute in the equation, we will get P total equals P01 chi1 plus P02 1 minus chi1. This we can write it as P01 chi1 plus P02 minus P02 chi1. Here we can take chi common, chi1 P naught 1 minus P naught 2 plus P naught 2 is the total vapor pressure of a binary solution. This is basically Raoult's law. That is what they have given here. Seeing the first equation here, we see that only one component's mole fraction here. Based on that, we can see total vapor pressure of a solution can be rated to the mole fraction of any one of the component. Total vapor pressure of the solution varies linearly with the mole fraction of the component 2. Basically, they are saying P is directly proportional to mole fraction. Basically the same thing, similar thing we saw in case of Henry's law as well, where they said pressure is directly proportional to dissolution, but here it is a bit different. The core formula is same as proportionality, pressure is directly proportional to mole fraction, but there it is the partial pressure of the gas and solubility of the solution, I mean gas in the liquid, but here it is partial pressure or not partial pressure, the vapor pressure of the liquid and mole fraction of the liquid in a binary solution. Even though it is a base concept is base proportionality is same, but the actual pressure and the chi values or the quantities which we take are different. This is a plot or a graph, the plot of vapor pressure and mole fraction of an ideal solution at constant temperature. The dashed lines 1 and 2 represent the partial pressure of the components. It can be seen that the plot P1 and P2 are directly proportional to chi1 and chi2 respectively. The total vapor pressure is given by the marked third line in the figure. Basically, they took a graph of pressure versus mole fraction, where mole fraction is the x-axis, vapor pressure is the y-axis. Here, in case of the first component, actually there's a second component. Second component, we know that partial pressure, or I mean vapor pressure, is directly proportional to mole fraction. So the graph should be linear, as it should be. It is also linear here as well. Linear. And here in case of the solution 2 as well, it is also linear. And this line represents the total vapor pressure, which is the sum of the individual vapor pressures. That is what they said here in the... Okay, the third one we understand from the Raoult's law is depending on the vapor pressures of the pure component 1 and 2, total vapor pressure over the solution decreases or increases with the increase of the mole fraction of component 1. Okay, a plot of P1 or P2 versus the mole fraction chi1 and chi2 solution gives linear plot as shown in figure 1.3. These lines 1 and 2 pass through the points for which chi1 and chi2 are equal to unity. Similarly, the plot line 3 of P total versus chi2 is also linear. As I described the graph, they are also describing it once again. The minimum value of P total is P1 pure, and the maximum value of P2, assuming component 1 is less volatile than 2. The minimum value of P total is P pure 1, and the maximum value of is P pure 2, assuming the component 1 is less volatile than component 2, that is P1 is less than P2. Okay, fine. Fine. As for why we can take the maximum value, seeing this graph where P2 has a higher linear higher vapor pressure compared to they describe these two statements, these two sentences actually. The minimum value here we see it is for P1 and the maximum value is P2. The vapor pressure is higher for P2 compared to P1. That is what they're saying there. We can, why that is so, we can attribute it to being the P1 being less volatile compared to the P2, not P2. Basically the solution or component 1 being less volatile compared to component 2. The composition of vapor phase in equilibrium with the solution is determined by the partial pressure of the components. The composition of vapor phase in equilibrium with the solution is determined by the partial pressures of the components. Okay, if y1 and y2 are the mole fractions, the composition of vapor phase in equilibrium composition meaning how much amount of vapor pressure that is equilibrium with the solution. This is the higher the partial pressure, higher the vapor phase, because the vapor pressure or the vapor phase is what causes the partial pressure. No, basically I think they are saying is this statement states that in a solution, if we take composition of vapor phase in equilibrium with the solution, partial pressure is the pressure of that component in the vapor phase itself. Okay, if this is the solution, this is the vapor phase, and in this vapor phase this is the A plus B solution, A and B components. So partial pressure of A, if it is higher, then vapor pressure is also higher. I mean, it is not vapor pressure, the vapor phase, higher the partial pressure, we can say that more molecules of the A component are in the vapor phase. That means the vapor pressure of, the partial pressure of A should also be high. And this also, if in a closed beaker or container, the equilibrium between these molecules and the solution also depends on this partial pressure of A and vapor phase. As higher the number of A components, the higher the equilibrium with A component and the solution. I think that is what the statement means. Okay, fine. If y1 and y2 are the mole fractions of the components 1 and 2 respectively, okay, in the vapor phase, then using Dalton's law of partial pressure, Dalton's law of partial pressure said that the total pressure of the solution in container will be a sum of the partial pressure of the component of the solution is given. Basically P total equals P1 plus P2. Then P1 according to Raoult's law, Okay, I had a confusion here, that is about here the y1 and y2 are not are they specifically gave that y1 and y2 are the mole fractions of the components 1 and 2 respectively in the vapor phase. I missed this vapor phase here. Basically they are saying that the y1 and y2 are mole fractions in the vapor phase, meaning when y1 equals the partial pressure of component 1 by P total, and here we get, due to that equation we get y1 equals P1 by P total, and when we know by Raoult's law that the partial pressure is chi1, where chi1 is a mole fraction in a liquid phase, times P naught 1 by, basically we will get this equations substituting the Raoult's law, and of course Dalton's theory as well, where P total equals P1 plus P2. This is the partial pressures. As for why does this matter, the partial pressure in the vapor phase doesn't actually depend on the more amount of the substance present in the solution. Even if a solution contains more amount of the substance, the vapor pressure partial pressure doesn't depend on the amount of substance in the liquid, but it depends on the volatile nature of the substance. The higher the volatile nature of the substance in the solution, the higher the partial pressure that component will contribute to the total pressure. Okay, that is why we got these equations, where P1 equals y1 P total, where we took this P total to the left hand side, and P2 equals y2 P total. In general, P1 equals yi times P total. Okay, vapor pressure of chloroform and dichloromethane at 298 Kelvin are 200 mm Hg and 450 mm Hg respectively. Calculate the vapor pressure of solution prepared by mixing 25.5 gram of CHCl3 and 40 gram of CH2Cl2 in 298 Kelvin, and mole fraction of each component in vapor phase. Basically, 1, they gave values of 200 mm and 450 mm. This is P01 and P02 values. They gave P naughts. The Raoult's law states that partial pressure equals P naught times the mole fraction, and they gave the amount of substance and the molecular formula of chloroform, and the amount of substance and the molecular formula of dichloromethane. With this we can find the number of moles, which we will get the the total mole fraction of each of these. Then we know that from Dalton's partial pressure, we know that the total partial pressure is equal to the total vapor pressure is equal to the sum of the individual partial pressures. And when we calculate using Raoult's law, we calculate individual partial pressures of both chloroform and dichloromethane. Both we add, we will get the total vapor pressure. That is the answer to the first question, the total vapor pressure of the solution. And the second question, mole fractions of each component in vapor phase. Basically they are not asking about in the liquid phase, they are asking in the vapor phase. So partial pressure of each in the vapor phase, we use the Raoult's law. Partial pressure equals P naught times chi A for PA, for A component. So in the process of finding the first answer itself, we will, because we need to find this individually and add them to get the total vapor pressure. So in this solution itself, we will get the answer for individual vapor pressures as well, individual partial pressures as well. Wait, no, they asked mole fraction, so no. So basically we are going to divide the, no, this is not the value for mole fraction of vapor pressure. We divide the PA value by the P total value. This will give us the total vapor mole fraction of the vapor in the vapor pressure phase. Vapor pressure phase. So molar mass of CH2Cl2, we get 885 gram per mole, and molar mass of chloroform is 120 gram per mole. And moles we can calculate via this, as they give the weight of the substance. When we get moles of dichloromethane to be around 0.5 and chloroform to be around 0.2, the total being around 0.7, then we'll get the mole fraction, which is around 0.7 for dichloromethane and 0.3 for chloroform. And using Raoult's law, we can get the total vapor pressure, which is around 347.9 mmHg. Then we will find individual vapor pressures. Individual vapor pressures are around 285.5 mmHg for dichloromethane and 62.4 for chloroform. Trichloromethane and or chloroform. Here we see that the vapor pressure or partial pressure of chloroform is actually very less compared to the vapor pressure of dichloromethane. Maybe this means that chloroform is less volatile compared to dichloromethane. I know that we have taken a more amount of dichloromethane and less amount of chloroform, but still it is less than double of the amount. It's not even double of the amount we have taken, but still the difference in the pressure or partial pressure is more than 2 times. Since CH2Cl2 is more volatile component than CHCl3, actually we can see this from the pure vapor pressure itself, where the pure vapor pressure of dichloromethane is 415 and chloroform is around 200 mm. And the vapor phase is also richer in CH2Cl2. It may be thus concluded that at equilibrium, vapor phase will always be rich in component of which is more volatile. Okay, that is a statement. Raoult law acts as a special case of Henry's law. To 15 more pages to go. Fine. Okay, Raoult's law as a special case of Henry's law. According to Raoult's law, the vapor phase of volatile component in a given solution is given by Pi equals mole fraction times the pure pure pressure of the component, the solution vapor pressure of the component. The solution of a gas in a liquid, one of the components is so volatile that it exists as a gas, and we have already seen that its solubility is given by the Henry's law, which states that P equals Kh times chi. If we compare the equations for Raoult's law and Henry's law, it can be seen that the partial pressure of the volatile component or gas is also directly proportional to its mole fraction in the solution. Only the proportionality constant Kh differs from Kh is different from the pure vapor pressure. Thus, Raoult's law becomes a special case of Henry's law in which Kh becomes equal to P naught. Vapor pressure of solutions of solids in liquids. Another important class of solution consists of solids in liquids. Solids that are dissolved in liquids. For example, sodium chloride, glucose, urea, cane sugar in water, and iodine and sulfur dioxide, sulfur dissolved in carbon disulfide. Some physical properties of these solutions are quite different from those of pure solvents. For example, vapor pressure liquids at a given temperature vaporize under equilibrium conditions. The pressure exerted by the vapor pressure of the liquid over the liquid phase is called vapor pressure. Wait. Basically, they are saying we can see vapor pressure of solutions or solids in liquids. Okay. And they are saying some of the physical properties of the solutions of these solid in liquid solutions. These are quite different from those of pure solvents. Okay, they are not comparing liquid solutions to solid liquid solutions here. They are comparing solid liquid solutions to pure solvents. For example, this is actually somewhat a hint to the colligative properties relation here. For example, vapor pressure, liquids at a given temperature vaporize, and under equilibrium conditions, the pressure exerted by the vapors of the liquid over the liquid phase is called vapor pressure. Basically, the under equilibrium conditions, the pressure exerted by the vapors of the liquid over the liquid phase is called vapor pressure. Okay, let's see the figure first. 1.4 A and B, decrease in the vapor pressure of the solvent on account of the presence of solute in the solvent. A, evaporation of the molecules of solvent from its surface is denoted by the blue particle. Blue particle is the solvent particles. In a solution, solute particles have been denoted by green particle, and they also occupy part of the surface area. Okay, in here this is a pure solvent. In this case, more number of solvent particles are evaporating, more vapor pressure. But in this case, when the surface area is also occupied by the solute molecules, which may or may not be more volatile, in such a case, the total vapor pressure due to less solvent molecules comparatively decreased. This here we saw it was total of 8 particles or more than 10 to 12 particles depending on the gas. Here there are only 4 particles here. Basically, as we added the solute, the vapor pressure decreased. In a pure liquid, the entire surface of the entire surface is occupied by the molecules of the liquid. If non-volatile solute is added to the solvent, basically like here in this pure solvent, the surface is completely occupied by the solvent molecules. But if a non-volatile, the solute is non-volatile, is added to a solvent given this solution, the vapor pressure of the solution is solely from the solvent alone, because this is a non-volatile solute and this does not get converted to vapor and does not contribute to the vapor pressure. And because of that, solvent molecules solely contribute to the vapor pressure. This vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. In the solution, the surface has both solute and solvent molecules. Thereby, the fraction of the surface covered by a solvent molecule gets reduced. The surface area of the solvent molecules is reducing. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced. As less the surface area, less the amount of solvent molecules escaping. Thus, the vapor pressure is also reduced. The vapor pressure is also reduced. The decrease in the vapor pressure of the solvent depends on the quantity of non-volatile solute present in the solution. as higher the number of non-volatile solute molecules, the lesser the more the decrease in the vapor pressure, or the lesser the vapor pressure. Irrespective of its nature, it does not depend on the nature of the solute, nature of the solvent. It only depends if the solute is non-volatile and if it is decreasing the, no, it will decrease the, the vapor pressure of the solution. For example, decreasing the vapor pressure of water by adding 1 mole of sucrose to 1 kg of water is nearly similar to that of produced by adding 1 mole of urea to the same quantity of water at the same temperature. Raoult's law in its general form can be stated as: for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. In a binary solution, let us denote the solvent by 1 and solute by 2. When the solute is, this is not a quantity but this is a denotation, we can take it as solvent as A and solute as B as well, but here they took it as 1 and 2. Only the solvent molecules are present in vapor phase and contribute to vapor pressure. Let P1 be the vapor pressure of the solvent, Chi1 be its mole fraction, and P01 be its vapor pressure in its pure state. Then according to Raoult's law, P1 is directly proportional to Chi1 and P1 equals Chi1 P01. The proportionality constant is equal to the vapor pressure of the pure solvent. So P01, a plot between the vapor pressure and a mole fraction of the solvent, is linear. As the mole fraction of the solvent decreases, the total vapor pressure, here there is only one contributing factor. In such a case, the total vapor pressure increases as the volatile component concentration increases. Higher the mole fraction of the volatile component, higher the vapor pressure of the total solution, because a non-volatile solute, it is not providing or contributing to the vapor pressure. In such a case, the total vapor pressure is only depending on the volatile component. This is the graph between mole fraction and vapor pressure. It is linear according to Raoult's law. The partial pressure depends on the mole fraction, so it is a linear graph. Vapor pressure of pure solvent. If solution obeys Raoult's law for all concentration, its vapor pressure would vary linearly from 0 to vapor pressure of the pure solvent. And now we come to ideal, non-ideal solutions. Not everything can be ideal in reality, so that is why you are reading such a concept. Liquid solutions can be classified into ideal and non-ideal solution on the basis of Raoult's law. Ideal solutions, the first topic, the solutions which obey Raoult's law. The solutions which obey Raoult's law over the entire range of concentration are known as ideal solution, meaning any concentration it obeys the Raoult's law, meaning partial pressure is directly proportional to mole fraction. Such a solution is called as ideal solution. The ideal solutions have two other important properties. The enthalpy of mixing of the pure component to form the solution is 0, and the volume of mixing is also 0. Basically, there should be no volume change, there should be no enthalpy change. It means that no heat is absorbed or evolved when the components are mixed. No volume change should be there should be no volume change. If the initial, before mixing, each A component was 100 ml and B component was 100 ml, when we mix also, the ideal solution should have a 200 ml concentration, 200 ml of volume. As for why this changes in non-ideal solutions, it's due to intermolecular attractions, where the attraction can reduce or the repulsion can increase the volume. In case of ideal solutions, such things cannot happen, and the delta volume mix and the delta enthalpy mix should be 0, meaning the volume of the solution would be equal to the sum of the volumes of the two components. At molecular level, ideal behavior of the solutions can be explained by considering two components A and B. At molecular level, ideal behavior of the solutions can be explained by considering two components A and B. In pure components, the intermolecular attractive interactions with the B of types A and BB, whereas in the binary solution, in addition to these two interactions, there will be AB type of interactions. In a pure solution, if we take A solution or B solution, we have the interactions between the A molecules in the A solution and BB molecules in the B solution. But when we mix them, in addition, we see both A and BB interactions as well, but we also see AB interactions. These interactions will also be present. If the intermolecular attractive forces between AA and BB are nearly equal to those of AB interactions, this leads to the formation of ideal solution. When the individual components molecular reactions interactions are equal to the different components molecular interactions, then we call that solution as an ideal solution. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. Solution of mixture of N-hexane and N-heptane, basically N meaning there are straight chain of hexane and heptane, bromoethane and chloroethane, benzene and toluene, etc. fall into the category of the ideal solutions. Now let's come under non-ideal solutions. When a solution does not obey Raoult's law or the entire range of concentration, then it is called a non-ideal solution. The vapor pressure of such a solution is either higher or lower than the predicted by Raoult's law. What this is actually saying is, when a solution does not obey Raoult's law or the entire range of concentration, then when it is obeying in entire range of concentration, it is called as ideal. When it is not obeying over the entire range of concentration, then it is called a non-ideal solution. The vapor pressure of such a solution is either higher or lower than the predicted Raoult's law. If it is higher, the solution exhibits a positive deviation. If it is lower, it exhibits a negative deviation from Raoult's law. This is understanding and obvious. If the vapor pressure, the total vapor pressure of the solution is more than what we expected, it is called positive deviation, where it is increasing from our expectations. And when it is exhibiting a lower vapor pressure than expected, then it is showing negative deviation. The plots of vapor pressure as a function of mole fractions for solutions are shown in figure 1.6. The vapor pressures of two component systems as a function of composition. A solution that shows positive deviation from Raoult's law. B, a solution that shows negative deviation from Raoult's law. These straight lines are the expected, but they show a curve like this here as well, and a bulging here as well. This is positive deviation, and a lower bulging in this case. This is the negative deviation. The cause of these deviation lie in the nature of the interactions at the molecular level. Why this happens is because in case of the positive deviation from Raoult's law, AB interactions are weaker than those of AA interactions or BB interactions. That is, in this case, the intermolecular attraction force between solvent molecules are weaker than those of solute and solvent molecules. This means in such solutions, the molecules of A or B will find it easier to escape than in pure state. Basically, when AB interactions are weaker, attraction forces are weaker, then the vapor pressure will also increase, because they will be able to vaporize easily or evaporate easily. This will increase the vapor pressure. That is why in the positive deviation we see a increase in the expectations. Pressure and result in positive deviation. Mixtures of ethanol and acetone behave in this manner. Ethanol and acetone An example for the non-ideal positive deviation solutions in pure ethanol molecules. In pure ethanol, molecules are hydrogen bonded, strong attraction bonded. Strong hydrogen bonding, meaning strong attraction forces. On adding acetone, its molecule gets in between the host molecules and breaks some of the hydrogen bonds between them. And by adding acetone, this molecule, acetone molecules, will reduce the hydrogen bonding in the ethanol molecules. Due to the weakening of the interactions, the solution shows positive deviation from the Raoult's law. In a solution found by adding carbon disulfide to acetone, the dipolar interactions between solute molecules are weaker than the respective interactions among the solute and solvent molecules. In a solution formed by adding carbon disulfide to acetone, the dipolar interaction between solvent molecules are weaker than the respective interactions among us. This also shows positive deviation because AB interactions are lesser than the AA and BB interactions. This is in case of positive deviation, in case of when a polar molecule which is able to form hydrogen bonds, polar plus non-polar in case of disulfide, and acetone plus non-polar gives positive deviation. Basically, polar plus non-polar, because of the breaking of bonds, hydrogen bonding in the polar molecules, polar and non-polar show positive deviation, whereas polar and polar show negative deviation, because polar and polar molecules can increase the hydrogen bonding, and this will cause an increase in the total attraction forces, and in such a case the vapor pressure decreases, so we see a negative deviation. And in case of non-polar and non-polar, we see no deviation. These are somewhat the ideal solutions. In case of benzene and toluene, those are non-polar and they don't show any deviation. Ideal solutions example is benzene and toluene, they are non-polar. Bromoethane and chloroethane, they are polar but they don't have any hydrogen bonding and such, I think. And N-heptane and N-hexane, those are also non-polar. So they have, I think they show positive okay, both are polar, it shows. What about non-polar and non-polar? weak van der Waals forces. These show, as I said before, these show ideal behavior. There is not much significant deviations. In the carbon disulfide, which is non-polar, and acetone, the solution also show positive deviation. In case of negative deviations from Raoult's law, the intermolecular attractive forces between A and BB are weaker than those of A and B interactions, leading to decrease in the vapor pressure, resulting in negative deviation. An example of this type of mixture is phenol and aniline, which due to OH and NH2 hydrogen bonding increase in the intermolecular hydrogen bonding between phenolic proton and lone pair of nitrogen atoms of aniline is stronger than the respective intermolecular hydrogen bonding between similar molecules. Similarly, a mixture of chloroform and acetone forms a solution with negative deviation from Raoult's law. This is because chloroform molecules is able to form hydrogen bond with acetone molecules as shown. Basically, chloroform can form hydrogen bonding with acetone molecules like this. Due to this, they show negative deviation because it increases the interaction forces and decreases the vapor pressure. This decreases the escaping tendency of molecules for increase in attraction forces, decrease in vapor pressure. This decreases the escaping tendency of molecules for each component, and consequently the vapor pressure decreases, resulting in negative deviation from Raoult's law. Some liquids on mixing form azeotropes, which are binary mixtures having same composition in liquid and vapor phase and boil at a constant temperature rate. Let's see the before statement. Before this decreases the escaping tendency of molecules for each component, and consequently the vapor pressure decreases, resulting in negative deviation from the Raoult's law. Okay, and the next statement is some liquids on mixing form azeotropes, which are binary mixtures having same composition in liquid and vapor phase and boil at constant temperature. They have same temperature, constant boiling temperature, and the composition is same in vapor phase as well, in both liquid and vapor phases as well. In such cases, it is not possible to separate the components by fractional distillation. Fractional distillation is done when the boiling point difference is around 10 Kelvin or 25 Kelvin, I think. Is the fractional distillation preferred? Difference in boiling point they have close boiling points. When the boiling point is less than 30 to 25 to less than 20 degrees, it is the point where we use distillation, fractional distillation. And these, because we can separate them using fractional distillation, these are not azeotropes. Solutions we can separate through via fractional distillation don't form azeotropes, and azeotropes can be separated by fractional distillation. There are two types of azeotropes called minimum boiling azeotrope and maximum boiling azeotrope. The solutions which show a large positive deviation from Raoult's law form minimum boiling azeotrope at specific composition. Large positive deviation means their vapor pressure is very high than expected, meaning their AB interactions are very weaker than AA and BB interactions. In such a case, they show large positive deviation, show minimum boiling azeotrope. Because their vapor pressure is very high, they have a minimum boiling point. as boiling point is defined as when the liquid's vapor pressure reaches 1 atmosphere of pressure. When the vapor pressure reaches at the temperature which the vapor pressure of a liquid reaches 1 atmosphere, that point is what we call as the boiling point. And for high vapor pressure liquids or solutions, the boiling point is less, so positive deviation, showing large positive deviation, they will be called as minimum boiling azeotropes, and this is at a specific composition. For example, ethanol water mixture obtained by fermentation of sugars or fractional distillation gives containing approximately 95% by volume of ethanol. Once this composition, known as azeotrope composition, has been achieved, the liquid and vapor have the same composition and no further separation occurs. The solution that show large negative deviation from Raoult's law from basically this statement, the above statement, they are saying when ethanol and water mixture is obtained by fermentation of sugars, then on fractional distillation we can separate till the ethanol's concentration by volume is 95% and 5% is water. Until this composition is acquired, we can separate them. But when this composition is acquired, where the ethanol reaches 95% volume by volume concentration from water, it is very hard to separate them by fractional distillation. It's not possible to separate them by fractional distillation because they become an azeotrope, and azeotropes have constant or same boiling point. In such a case, they cannot get separated. No further separation occurs in case of fractional distillation. The solution that show large negative deviation from Raoult's law form maximum boiling azeotrope. Negative deviation means less vapor pressure, so they need higher boiling point. So we call them as maximum boiling azeotrope at specific composition. Nitric acid and water is an example of this class of azeotrope. This azeotrope has approximate composition of 68% nitric acid and 32% water by mass, the boiling point of 393.5 Kelvin. I think the boiling point of nitric acid was 298 Kelvin. No. BP of nitric acid is in Kelvin. For 100% pure also, like, okay, so that is great here. Great to see that he gave both our concentration, required concentration here 68%, and it's 68% concentrated in the azeotropic. At this stage, azeotrope is formed and the boiling point is around 356.15 Kelvin. Even though water contains around 32% by mass is water, the boiling point is water is 373 Kelvin, but due to HNO3 it is reduced to 356.15 Kelvin. This shows a negative deviation. The vapor pressure of in-text question, the vapor pressure of pure liquids A and B are 450 and 700 mmHg respectively at 350 Kelvin. Find out the composition of the liquid mixture. Find out the composition of the liquid mixture if total vapor pressure is 600 mmHg. Basically, Raoult's law, when we add both of them, and they give P naught values, and we need to find the total pressure. Now, one of the main topics of colligative properties and determination of molar mass. This question is basically using the Raoult's law. We will get the answer if we use the Raoult's law. We have learned in section 1.4.3 that the vapor pressure of a solution decreases when a non-volatile solute is added to a volatile solvent. There may be many properties of solutions which are connected with this decrease of vapor pressure. These are relative lowering of vapor pressure of the solvent, depression of freezing point of the solvent, elevation of boiling point of the solvent, and osmotic pressure of the solution. We saw lowering of vapor pressure. It is lowered because we saw the details in the before topic. And as for depression, in reducing of freezing point, ethylene glycol is added as an anti-freeze agent. It decreases the freezing point. And elevation of boiling point of the solvent, it is due to as the vapor pressure decreases, and vapor pressure and the temperature at vapor pressure reaches 1 atm is boiling point. So as the vapor pressure decreases, the amount of vapor pressure to reach 1 atm at the temperature increases, so the boiling point decreases. Osmotic pressure of the solution, that is the fourth colligative property. All these properties depend on the number of solute particles irrespective of the nature of the solute particles, solvent particles, and relative and of their nature, irrespective of their nature, relative to the total number of particles in the solution. They only depends on the total number of particles in the solution. Such properties are called colligative properties, the properties which depend only on the number of the particles. Colligative from Latin, co means together, ligare means to bind. In the following sections, we will discuss these properties one by one. The first is relative lowering of vapor pressure. We have learned in section 1.4.3 that vapor pressure of a solvent in solution is less than that of the pure solvent. Raoult established that the lowering of the vapor pressure depends only on the concentration of the solute particles, and it is independent of their identity. Given in section establishes a relation between vapor pressure of the solution, mole fraction, and the vapor pressure. P1 equals chi1 P0. Reduction in the vapor pressure of the solvent, delta P1, is given as delta P1 equals P01 minus P1 equals P01 minus P01. The change in vapor pressure they are giving it as, and the pure it is P0. So P initial minus P pure is P initial minus P final, and we know that P partial pressure is chi1 P0. So in such a case, the change in vapor pressure is P0, the P pure value, times 1 minus chi1. Knowing that chi2 equals 1 minus chi1 reduces the equation to 1 minus chi1 equals chi2 in a binary solution. So chi2 is the mole fraction of the non-volatile solute. In the change in, so we get that a change in partial pressure or vapor pressure is equal to chi2 P1 naught, meaning this is the relative lowering of vapor pressure formula, and we shift this to that side, we will get P pure minus P1 by P0 equals chi2. In a solution containing several non-volatile solutes, the lowering of the vapor pressure depends on the sum of the mole fraction of different solutes. Equation 1.24 can be written as delta P1 by P01 equals P01 minus P1 by P01 equals chi2. The expression on the left hand side of the equation, as mentioned earlier, is called relative lowering of vapor pressure and is equal to the mole fraction of the solute. This is the main equation of this topic. The above equation can be written as, because we are basically substituting the mole fraction value, which is N2 by N1 plus N2, P0 minus P1 by P0. Here N1 and N2 are the number of moles of, N2 is the number of moles of solute and N1 is the number of moles of solvent present in the solution. For a dilute solution, N2 is very small than N1, so we can neglect N1. We can neglect N2, the number of moles of solute in the denominator. Then we will get N2 by N1 equals change in vapor pressure by the original vapor pressure. Then we know that given weight by molecular weight gives us the number of moles. Substituting that formula, we will get another form of the same equation in another way. Here W1 and W2 are the masses meaning given weight, and M1, capital M1 and capital M2 are the molar masses of the solvent and solute respectively. From this equation 1.28, knowing all other quantities, the molecular mass of the solute M2 can be calculated. This is the question. The vapor pressure of pure benzene at a certain temperature is 0.85 bar. A non-volatile, non-electrolytic solid weighing 0.5 grams when added to 39.0 gram of benzene, molar mass of benzene, they gave it as 78 gram per mole. And vapor pressure of the solution then is 0.845 bar. So the change in vapor pressure is 0.05 bar. What is the molar mass of the solid? They gave us specifically that it is a non-volatile and non-electrolytic solvent. Non-volatile they gave specifically because it shouldn't mess with the vapor pressure. We here consider that it is completely non-volatile and doesn't contribute to the vapor pressure. But if it contributes to the vapor pressure, then we should use a complete Raoult's law instead of this partial one. Here we directly consider that the vapor pressure of the solute is 0. It's not contributing to the vapor pressure at all. So we take it as non-volatile, completely non-volatile, and non-electrolytic because electrolytic solutes can dissociate to give the actual value to be if NaCl, 1 mole of NaCl to gives 2 moles of ions, 1 mole of Na and 1 mole of Cl minus, sodium and chloride ions. So the total mole fraction changes for an electrolytic solid. That is why they gave it specifically for a non-electrolytic solid. As for the electrolytic solid, we will have a new case under the same chapter. It is called, we are going to introduce the Van 't Hoff's factor, that we are going to read then. Various quantities known to us are as follows. P01 equals this is okay. Then substitute in the above equation, direct formula, direct substitution, direct answer. Now the second colligative property is elevation of boiling point. The vapor pressure of liquid increases with increase in temperature. It boils at temperature at which its vapor pressure is equal to the atmospheric pressure. The vapor pressure of a liquid increases with increase in temperature. Okay. It boils at the temperature at which its vapor pressure is equal to the atmosphere pressure. For example, water boils at 373.15 Kelvin because at this temperature the vapor pressure of water is 1.013 bar, basically 1 atmosphere. We also learned that in the last section that the vapor pressure of the solvent decreases in the presence of non-volatile solute. 1.7 depicts the variation of vapor pressure of pure solvent and solution as a function of the temperature. For example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373 Kelvin. In order to make this solution boil, its vapor pressure must be increased to 1.013 bar by increasing the temperature, the pure solvent. Thus, the boiling point of solution is always higher than the boiling point of the pure solvent in which the solution is prepared, as shown in figure 1.7. Basically, let's see the figure. The vapor pressure curve for solution lies between the curve for pure water. The diagram shows that delta boiling point, change in boiling point, denotes the elevation of boiling point of a solvent in solution. They took vapor pressure with temperature at x-axis and vapor pressure at y-axis. Solution is actually having a higher boiling point here, and so solvent has a lower boiling point, and the vapor pressure as well. The solvent has a little lower vapor pressure. No, the solvent is at a lower temperature, whereas the solution is at a higher temperature, and they reach the same vapor pressure at different temperatures. Similar to the lowering of vapor pressure, the elevation of boiling point also depends on the number of solute molecules. Okay, elevation of boiling point also depends on the number of solute molecules. That is why it's under the colligative properties. This doesn't depend on their nature. A solute of 1 mole of sucrose in 1000 gram of water boils at 373.52 Kelvin at 1 atmospheric pressure. Let T0 be the boiling point of pure solvent and Tb be the boiling point of solution. The increase in the boiling point, delta Tb equals Tb minus T0, is known as the elevation in boiling point. Experiments have shown that for dilute solutions, the elevation of boiling point is directly proportional to the molar concentration of the solute in a solution. This is for dilute solutions. The elevation in boiling point is directly proportional to the molarity or the molar concentration of the solute in the solution. And delta Tb is directly proportional to molarity. Then we can introduce a proportionality constant, which is Kb, which is the boiling constant, boiling point elevation constant or molar elevation constant. Small m is molarity, is the number of moles of solute dissolved in 1 kg of solvent, and the constant of proportionality Kb is called boiling point elevation constant or molar elevation constant, ebullioscopic constant, ebullioscopic constant. The unit of Kb is Kelvin kg per mole. Values of Kb for some common solvents are given in table 1.3. I'll see the table later. W2 gram of, basically W2 is the weight gram of the solution or solute of mass. M2 is dissolved in W1 gram of solvent. Then molarity of the M of the solution is given by, it's basically molarity formula they are revising again here. Substituting the value of molarity in equation 1.30, this equation, we get that Kb times 1000 times W2 by M2 and M2 times W1, where we took 1000 because it is in grams. We don't need to take 1000 if it is in kgs, but in case of grams we take it as 1000. The M2 is the molecular weight of the solute, molar mass of the solute, known mass of solute is known as the mass of the solvent is taken, and delta TB is determined experimentally for shown solvent whose KB value is known. This is basically an easy question based on the same principle. Let's see the question. 18 gram of glucose, they give the molecular formula of glucose to be around, they did not give the molecular mass, sorry. They gave the molecular formula C6H12O6. It is dissolved in 1 kg of water in an apparatus, which is saucepan. At what temperature will water boil? At 1.013 bar, where Kb or molar elevation constant for water 0.52 Kelvin kg per mole. They're asking us to find the change in elevation boiling point, the change in boiling point, how much the boiling point is elevated, and the final boiling point when 18 gram of glucose is added to 1 kg of water. In such a case, what will be the final boiling point? And the calculated answer is 0.052 Kelvin is the change, and the change is very, very minute. So from 373.15 to, due to adding 18 grams of solute of glucose, we will increase the boiling point to 373.202. Okay. The boiling point of benzene is 353.23 Kelvin when they give the boiling point, normal boiling point, when 1.80 gram of non-volatile solute was dissolved in 90 gram of benzene. Okay, then boiling point is raised to 354.11 Kelvin, 0.88 Kelvin change. Calculate the molar mass of the solute. Kb for benzene is 2.53 Kelvin kg per mole. They gave the molar elevation constant. We can calculate the change in boiling point through the given two boiling points. They gave the mass of benzene dissolved, and they gave the amount of non-volatile solute which is dissolved. They are asking us to find the molar mass of the solute, which we get it to be around 58 grams. Now the third colligative property is depression in freezing point. Diagram showing delta F depression in the freezing point of a solvent in a solution. This is the vapor pressure and temperature. The liquid solvent, the pure solvent, it gets frozen at a higher temperature when compared to the solution, which gets frozen at an even lower temperature than compared to the solvent. This is what we call as depression in freezing point. And in this state, where the normal, in this temperature where the normal pure solvent is frozen, the solution is still liquid. It's actually in a perfect equilibrium, and as we go down it will freeze. The lowering of vapor pressure of a solution causes a lowering of the freezing point compared to that of the pure solvent. We know that at the freezing point of a substance, the solid phase is in dynamic equilibrium with the liquid phase. Thus, the freezing point of a substance may be defined as a temperature at which the vapor phase of the substance is the vapor pressure of the substance in its liquid phase is equal to its vapor pressure in its solid phase. In the boiling point can be defined as the vapor pressure of liquid in its reaching its atmospheric pressure, but freezing point is reaching the solid phase vapor pressure. A solution will freeze when its vapor pressure equals the vapor pressure of the pure solid solvent, as it is clear from figure 1.8. According to Raoult's law, when a non-volatile solid is added to the solvent, its vapor pressure decreases and now it would become equal to the solid solvent at lower temperature. Thus, the freezing point of the solvent decreases. Okay. Let T naught F be the freezing point of pure solvent. Basically, due to addition of a non-volatile solvent solute, the temperature required to decrease the vapor pressure of the liquid to be reaching its equal to its solid's vapor pressure is taking more temperature than required. I mean less temperature than required, than normal actually. Because of that, the freezing point is decreasing. Let T naught F be the freezing point of pure solvent and Tf be the freezing point when non-volatile solute is added or dissolved in it. Then decrease in freezing point delta F equals T naught F minus Tf is known as the depression in freezing point. Similar to elevation of boiling point, depression in freezing point delta Tf for dilute solution, ideal solution, is directly proportional to molality. I'm not sure why they say it is. I think they said it is experimentally found out that only in dilute solution this change is proportional to molality. Delta F equals Kf, where Kf is the molar depression constant or freezing point depression constant. The proportionality constant Kf, which depends on the nature of the solvent, is known as freezing point depression constant or depression constant of the depression constant, or even cryoscopic constant. Ebullioscopic for molar elevation, cryoscopic for constant, freezing point depression constant. But they gave that the proportionality constant, this depends on the nature of the solvent. Okay, this depends, but the total depression in freezing point due to the total colligative property doesn't depend on the solvent, but the freezing point depression constant, the cryoscopic constant, does depend on the nature of the solvent. The unit of Kf is Kelvin kg per mole. This is the same as the ebullioscopic constant. Values of Kf for some common solvents are listed in table 1.3. If W2, basically molality, again solute having molar mass as M2 present in W 1 gram of solvent produces a depression point, change in depression point, freezing point of delta Tf of the solvent. Then the molarity of the solute is given by the equation 1.31. Okay, substituting this value, molarity in equation, we get delta F, basically just substituting in the delta Tf is directly proportional to molarity and introducing a proportionality constant of cryoscopic constant, then we get this equation. Then 1000 is because we are substituting in case of grams. Final value for change is this equation, and when we want to find the molar mass of the non-volatile solute, we get this equation. Thus, for determining the molar mass of the solute, we should know the quantities of the weight or the masses, the change in temperature, the change in the depression of the freezing point, molar freezing point depression constant. The values of Kf and Kb, which depend on the same nature of solvent, can be ascertained from the following relations. This is the relation to find out the Kf value, where R is the gas constant, M1 is the molecular mass, I think, yeah, molecular mass of the solvent is the molecular mass of the solvent, and because it depends on the solvent itself, Kf and Kb depend the solvent nature of the solvent, and the normal, no wait, this is the final or the reduced freezing point, Tf square by 1000 times delta fusion enthalpy. And in the same formula in case of Kb, finding Kb as well, but just changes is made where freezing point is replaced by boiling point, the new boiling point, the elevated boiling point, and fusion enthalpy is replaced by vaporization enthalpy. Here the symbols R and M1 stand for the gas constant and molar mass of the solvent respectively, and Tf and Tb denote the freezing point and boiling point of the pure solvent respectively in Kelvin. Okay, this Tf and Tb are not the new after dissolution of the solute, but before the pure boiling points and freezing points for the pure solvent. For the delta fusion enthalpy and delta, basically they represent enthalpies for fusion and vaporization of the solvent respectively. Solvent Okay, they gave some values for molal, the ebullioscopic and the cryoscopic constants here. These are for some solvents. For water, it is the boiling point is 373, the ebullioscopic constant is 0.53, freezing point is 273, which is 0 degree, 1.86, and if we see the uh, highest highest ebullioscopic constant is acetic acid, which has a 2.93 value, whereas the highest cryoscopic constant value we see in case of, no, wait, no, it's not acetic acid here. The ebullioscopic or the molar elevation constant highest we see in carbon tetrachloride. Carbon tetrachloride 5.03, and the highest cryoscopic constant we see in case of cyclohexane, which is around 20. Okay, this is a basic question. They ask the freezing point depression and the freezing point solution of the solution. So find freezing point using the formula and add the or decrease the value, then you will get the freezing point of the solution. 1 gram of non-alcoholic solution dissolved in 50 grams of benzene. Load the freezing point of benzene by 0.40 Kelvin. The freezing point depression constant of benzene is 5.12 Kelvin. Molar mass of the solute, same. The equation is there, substitute the value, you will get the answer. Where the, yes, here this. And next, the fourth property is osmosis and osmotic pressure, the fourth correlative property. There are many phenomena which we observe in nature at home. For example, raw mangoes shrivel when pickled in brine salt. I mean, brine meaning a concentrated salt solution, meaning when raw mangoes, when we add it to a brine solution, they get shriveled up. Basically, there is a loss of water, meaning the solution molecule, they go from higher concentration to the solute molecules, they go from higher concentration to lower the solvent molecules go from higher concentration to lower concentration. The salt water has a lower concentration of solvent molecules, not solute. Solute, it is the inverse, where solute, the concentration of brine is the highest, where mango has less concentration of solute, but water content, mango has the high water concentration, solvent concentration, and brine has the low solvent concentration. Because of that, the water moves from mango to salt solution, the brine solution, and it gets shriveled up, and we can say salt also diffuses into the mango. Wilted flowers revive when placed in fresh water. They gain the water from the solution. Blood cells collapse when suspended in saline water. I think they meant do not collapse when suspended in saline water or etc. If we look into these processes, we find one thing in common, that is all these substances are bound by membrane, a semi-permeable membrane. Let's see the diagram first. Level of the solution rises in the thistle funnel due to osmosis of solvent. This is the semi-permeable membrane, and this is the solvent, this is the solution. As solution has lesser amount of solvent, the solvent should go through the semi-permeable membrane into the solution, increasing the amount of the solution. So this should increase. These membranes can be animal or vegetable origin, and these occur naturally such as pig's bladder, or parchment, or can be synthetic such as cellophane. Parchment, finally with me. These membranes appear to be continuous sheets or films, yet they contain a network of submicroscopic holes or pores. They seem like continuous sheets, but they have pores. Small solvent solvent molecules like water can pass through these holes, but the passage of bigger molecules like solute is hindered. Membranes having this kind of properties are known as semi-permeable membranes. Assume that only solvent molecules can pass through these semi-permeable membranes. If this membrane is placed between the solvent and solution, the solvent molecules will flow through the membrane from pure solvent to solution. This process of flow of the solvent is called osmosis. The flow of the basically osmosis, another way of defining osmosis is the flow of water from high concentration to low concentration of the solvent molecules through a semi-permeable membrane. The flow will continue till the equilibrium is attained. Okay, till equilibrium. Okay, the flow of the solvent from its side to solution side across the semi-permeable membrane can be stopped if some extra pressure is applied on the solution. Okay, when we apply pressure, the osmosis will stop. This pressure that just stops the flow of solvent or osmosis is called osmotic pressure of the solution. The flow of solvent from dilute solution to the concentrated solution across a semi-permeable membrane is due to osmosis. This important point to be kept in mind is that solvent molecules always flow from a lower concentration to higher concentration of the solution. Basically, this is the lower concentration to the higher concentration. This is of the concentration of the solution, not the solvent. If in the solvent molecule, the solvent molecules will flow from the higher concentration of the solvent to the lower concentration of the solvent. But in case of the solution, if we take, it will flow from lower concentration to the higher concentration of the solution. The osmotic pressure has been found to depend on the concentration of the solution. This is the semi-permeable membrane. This is the atmospheric pressure, and here we apply, and this is the solution. So solvent molecules, they go from solvent to solution. So when we apply pressure here, the osmosis is stopped, and when this osmosis is stopped, that pressure is called osmotic pressure. Must be applied on solution side to prevent osmosis. Osmotic pressure of a solution is the excess pressure that must be applied to a solution to prevent osmosis, that is, to stop the passage of solvent molecules through a semi-permeable membrane into the solution. This is illustrated in figure 1.10. Osmotic pressure is a colligative property as it depends on the number of solute molecules and not on their identity. For dilute solutions, it has been found experimentally that osmotic pressure is proportional to the molarity. This is molarity and the given temperature. Thus, pi equals CRT, where pi is the osmotic pressure, C is the concentration or molarity, R is the gas constant, T is the temperature. R is the gas constant. And we know that molarity is the number of moles of solute by the volume per liter. This is also why to write the pi. Here V is the volume of the solution in liters containing N2 moles of the solute. If W2 grams of the solute is the molar mass, M2 is the present solution, then N2 equals W2 by M2, and we can write, basically they are substituting the formulas here. Yes, same thing repeated again. And this is for the osmotic pressure times volume, we will get this, and for the solute, the molar mass of the solute, we can get this equation. Thus knowing the, this is the molar mass of the solvent, this is the molar mass of the, no, this is the molar mass of the solute, not solvent. This is present only in the solution. Thus knowing the quantities W2, T, pi and V, we can calculate the molar mass of the solute. Measurement of osmotic pressure provides another method of determining molar masses of solutes. This method is widely used for determining the molar masses, proteins, polymers, and other macromolecules. The osmotic pressure method has the advantage over other methods as the pressure measurement is around the room temperature and the molarity of the solution is used instead of molality. As compared to other colligative properties, its magnitude is large even for very dilute solutions. The technique of osmotic pressure for determination of molar mass of solutes is particularly useful for biomolecules as they are generally not stable at higher temperatures and polymers have poor stability. Two solutions having same osmotic pressure at a given temperature are called isotonic solutions. When such solutions are separated by semi-permeable membrane SPM, no osmosis occurs between them. For example, the osmotic pressure associated with the fluid inside the blood cell is equivalent to that of 0.9% mass by volume sodium chloride solution. This is called a normal saline solution and it is safe to inject intravenously. Basically, osmotic pressure associated with fluid inside the blood cell. Basically, when we are taking injections into our blood, if it is not the solution is not isotonic solution, the blood cells will lose water content and it might lead to problems. So to avoid such situations, we use saline water which has 0.9% sodium chloride solution. Because due to the presence of this 0.9% mass by volume sodium chloride in the saline water or the normal saline solution, this will create an isotonic atmosphere inside the veins or blood veins or blood vessels. In such a case, no osmosis occurs and the injections will do its work and there is no interruption with the blood cells. On the other hand, if we place the cells in a solution containing more than 0.9% mass by volume sodium chloride, water will flow out of the cells and they would shrink. Such a solution is called hypertonic. If the salt concentration is less than 0.9%, the solution is said to be hypotonic. In this case, water will flow into the cells if placed in the solution and they would get swelled. This is basically, they gave this example. They gave 200 centimeter cube. This is the volume of an aqueous solution of a protein. Centimeter cube is the volume, okay, and this contains 1.26 grams of protein, okay. The osmotic pressure of such a solution is at 300 Kelvin is found to be 2.57 into 10 power minus 3 bar, okay, fine. They gave the osmotic pressure. Now calculate the molar mass of the protein. Fine, we substitute directly in the formula and we will get the molar mass. The phenomena mentioned in the beginning of this section can be explained on the basis of osmosis. Raw mango placed in concentrated salt solution loses water via osmosis and shrivel into a pickle. Wilted flowers revive when placed in a fresh water. Here, when a mango loses water, it is called a hypertonic solution. When a wilted flowers revive when placed in fresh water, this is a hypotonic solution. Water is getting into the flower. A carrot that has become limp because of water loss in the atmosphere can be placed in the water, making it once firm again, basically gaining of water, hypertonic solution once more. Water will move into cells through osmosis when placed in water containing less than 0.9% mass by volume salt. Blood cells swell due to flow of water in them by osmosis. People taking a lot of salt or salty food experience water retention in the tissue cells and intercellular spaces because of osmosis. The resulting puffiness of swelling is called edema. Okay, fine, this is a condition. We saw bends and edema here in two disorders or two conditions here, where people who take too much salt will have too much salt concentration. This will create a hypertonic No. But shouldn't more salt concentration create a hypertonic solution? Then shouldn't the cells lose water? Let's see. Swelling of cells due to osmosis in people taking high salt content. But wouldn't high salt content create a hypertonic solution? Which would decrease the water from cells. But why does edema swelling happen with high salt intake? And how systematically, not just a cellular level? High salt intake increases sodium in blood. This is the extracellular fluid. This makes blood hypertonic compared to tissues. Initially, they should pull water out of cells. You are correct about this local effect. But the body reacts to restore balance. This makes kidneys retain more water to dilute the excess sodium. The increase in blood volume and pressure. Increased blood pressure can cause fluid to leak from blood vessels into tissues. Okay, this leaked fluid accumulated in the interstitial space between cells, causing the edema, even though cells themselves may not be the one taking in more water. Okay, I understand. This is actually a counter mechanism of the body which is causing this swelling, not the actual hypertonic situation. Water movement from soil into plant roots and subsequently into the upper portion of the plant is partly due to osmosis. The preservation of meat by salting of fruits, by adding sugar products against bacterial action, by salting, basically salting, creating a hypertonic solution, taking the water, drying the meat, and fruits by adding sugar products against bacterial action. Though the process of osmosis, a bacterium on salted meat or candied fruit loses water, shrivels and dies. Reverse osmosis and water purification. This is one of the uses of osmotic pressure. The direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. That is, now the pure solvent flows out of the solution through the semi-permeable membrane. This phenomenon is called as reverse osmosis and is great practical utility. Reverse osmosis is used in desalination of seawater. A schematic setup for the process is shown in figure 1.11. Salt water, apply pressure, fresh water passes through a semi-permeable membrane. Water outlet, we get fresh water. When pressure more than osmotic pressure is applied, pure water is squeezed out of the seawater through the membrane. A variety of polymer membranes are available for this purpose. The pressure required for the reverse osmosis is quite high. A workable porous membrane is a film of cellulosic acetate placed over a suitable support. is a film of cellulosic acetate placed over suitable support. Cellulose acetate is permeable to water but impermeable to impurities and ions present in seawater. These days, many countries use desalination plants to meet their potable water requirements. Vapor pressure, the in-text questions. Vapor pressure of pure water at 298 Kelvin is 23.8 mmHg of urea. That much 50 gram of urea is dissolved in 850 gram of water. Calculate the vapor pressure of water for the solution and its relative lowering. Basically, this is the first colligative property, the exact formula used. Substitute in the formula and you will get the answer. Boiling point of water at 750 mmHg is 99.63 Celsius. How much sucrose is to be added to 500 gram of water such that it boils at 100 degrees? This is also the elevation in boiling point. We substitute a different value here and we will get the answer from the formula. Calculate the mass of ascorbic acid, vitamin C, C6H8O6 to be dissolved in 75 grams of acetic acid to lower its melting point by 1.5 degrees, where they gave the cryoscopic constant to be 3.9 Kelvin kg per mole. Also direct formula substitution. Calculate the osmotic pressure in pascals exerted by a solution of prepared by dissolving 1.1 gram of polymer of mass 185,000 1 gram of polymer of molar was 185,000. Okay, such a large molecule. You only dissolved 1 gram of it in 450 ml of water at 35 degrees. Okay, this is also direct formula substitution, pi equals CRT. Now the next main topics is the introduction of the abnormal molar masses, Van Hoff's factor, etc. There are how many pages? Total 2 pages for the theory and then example which is around 2 pages in itself and a summary. Total of 5 pages. Abnormal molar masses. We know that ionic compounds when dissolved in water turn into cations and anions. For example, if we dissolve 1 mole of KCl 74.5 grams in water, we expect 1 mole of each K plus and Cl minus ions to be released in the solution. If this happens, there will be 2 moles of particles in the solution. If we ignore the interionic attraction, 1 mole of KCl in 1 kg of water would be expected to increase the boiling point by 2 into 0.52 Kelvin to 1.04 Kelvin. Okay. Now if we did not know about the degree of dissociation, 0.52 is I think the ebullioscopic constant and 2 is the molality here, as it doesn't depend on the nature of the particle to be either ions or molecules. We take 2 times, so which is around 1.04 Kelvin. But if it was non-electrolyte, it would still stay in 0.52 Kelvin. That is for 1 molar. I mean 1 molal. Now, if we do not know about, in case of KCl, we know that that's 100%, it's a strong electrolyte. There is a 100% dissociation rate. So we can easily know we'll get 2 moles of solute when we dissolve KCl. But if we do not know about the degree of dissociation, we could be led to conclude that mass of 2 mole particles is 74.5 gram and the mass of 1 mole of KCl would be, include that mass of 2 mole particle is 7, mass of 1 mole of KCl would be, to write that the rule that when there is dissociation in solute and ions, the true value, the experimentally determined molar mass is always lower than the true value. Okay, 1 mole of particles of KCl is around, KCl dissolving itself will give 2 mole particles, which the whole mass is 74.5 grams. This is the whole mass of KCl. This is also 74.5 grams. But when only 1 mole of these particles, if we take, this is not KCl, that would be 37.5. And this brings into light the rule that when there is dissociation of solute into ions, the experimentally determined molar mass is always lower. This is a statement. This can be asked as a statement. Basically, they are saying when there is dissociation of solute into ions, the experimentally determined molar mass, okay, the one which we experimentally determine, the molar mass, it will be lower than the true value. Okay, fine. Molecules of ethanoic acid, acetic acid, dimerize, meaning they get bonded like this. Hydrogen bonding, if we see, this is a single acetic acid molecule. 1H, basically this much. This is one molecule, one acetic acid molecule. The second one is another molecule. Due to hydrogen bonding, they get dimerized. They form a dimer. This is due to hydrogen bonding. This normally happens in solvents of low dielectric constant. In this case, the number of particles is reduced due to dimerization. Association of molecules is depicted as follows. It can be undoubtedly stated that if all the molecules of ethanoic acid associate in benzene, then delta Tb and or delta FTF for ethanoic acid will be half of the calculated or normal value. The molar mass calculated on the basis of this delta Tb or delta TF will therefore be twice as the expected value. Such a molar mass that is either lower or higher than expected or normal value is called an abnormal molar mass. In 1880, here basically they're talking about the molecular mass. Here molecular mass, each molecule mass is actually a double here, but in case of KCl, each molecule ion mass is half of the actual one. It's not half actually, but it is abnormal. For normal, if we calculate, the molar mass will be twice the actual value. This is abnormal molar mass. In 1880, Van't Hoff introduced the Van't Hoff factor, which is depicted or denoted by I, known as the Van't Hoff factor, to account for the extent of dissociation or association. This factor, Van't Hoff factor, defined as I normal mass, I equals normal mass by abnormal mass, which can also be defined as observed correlative property by calculated correlative property. I equals Total number of moles after association or dissociation, number of moles before association or dissociation. For example, KCl, I can be I equals after association it is 2, before association it's 1. For KCl it is 2. I can be defined as normal molar mass by abnormal molar mass, observed colligative property by calculated colligative property, total number of moles or particles after dissociation or association, total number of moles of particles before association or dissociation. Here abnormal molar mass is experimentally determined. Molar mass calculated colligative properties are obtained by assuming that non-volatile solute is neither associated nor dissociated. Experimentally determined molar mass and calculated colligative properties are obtained by assuming that non-volatile solute is neither associated or dissociated. In case of association, value of I is less than unity, while for dissociation it is greater than unity. For example, the value of I for aqueous KCl is close to 2, while the value for ethanoic acid in benzene is nearly 0.5. Inclusion of Van 't Hoff factor modifies the equation for colligative properties. Relative lower vapor pressure of solvent. Here we add an I. Elevation of boiling point we add an I. Depression of freezing point we add an I. And of course for osmotic pressure solution as well we add an I. Table 1.4 depicts the values of the factor Van 't Hoff factor for several strong electrolytes. For KCl, NaCl, MgSO4 values approach 2. The solution becomes very dilute as expected. The value of I gets closer to 3 for K2SO4. These are the cases. This is the example question. Basically 2 grams of benzenoic acid dissolved in 25 grams of benzene shows a depression in freezing point equal to 1.62 Kelvin. Molar depression constant for benzene is 4.9 Kelvin. What is the percentage of association of acid if its dimer is in the solution? If it forms a dimer in the solution. Basically, okay, it forms a dimer, so I should be around 0.5. Given quantities, weight they gave 2 grams of benzenoic acid, then solvent weight also they gave 2 grams of benzene, 2 grams of 25 grams of benzene, and cryoscopic constant 4.9 Kelvin kg per mole, and the change in freezing point is 1.62 Kelvin. The experimental values we take it to be assumed there is no dimer. There is no dimerization as such. In such a case, M2 direct exact values we take, we will get it to be around 241.28. This is the abnormal. The experimental molar mass of benzenoic acid in benzene is 241.98 gram per mole, 242 approximately. Now consider the following equilibriums of the reaction. It gets dimerized. If X represents the degree of association of the solute, then we would have 1 minus X mole of benzene acid left in an unassociated form. Weight of the solute, then we would have that many less mole of benzenoic acid left in unassociated form, and correspondingly X by 2 associated moles of benzenoic acid at equilibrium. Therefore, the total number of moles of particles at equilibrium is 1 minus X plus X by 2 which is equal to 1 minus X by 2. Thus, total number of moles of particles at equilibrium, Van 't Hoff factor I equals normal molar mass by abnormal molar mass. which we calculated to be around, the normal should be 122, and abnormal is 241.98. Sure, get the factor, the Van House factor should be around 0.5, or it should be around 1. Therefore, degree of association of benzoic acid is 99.2%. They asked association of benzene, yes. Okay, next question. 0.6 ml of acetic acid CH3COH. Basically, this problem, mainly what we did is we found out abnormal mass, molar mass, and normal molar mass. Normal molar mass 122, which is around half of the 242. So you'll of course get 0.5 itself. And in case of 0.6 ml of acetic acid having density 1.06 gram per 6 gram per liter is dissolved in 1 liter of water. The depression and freezing point observed for this strength of acid was 0.0205 degree. Calculate the Van Hoff factor and the dissociation constant of the acid. Number of moles of acetic acid, which we will find through multiplying the density times the given volume by the molecular mass, which will get to be around 0.0106 mole or 0.01 mole. Molarity equals 0.0106 by the 1000 ml solution times 1 gram per mole. This is the density. We will get it around, molarity should be around 0.0106. Exact same, because for a 1 molar solution. And using the depression, the cryoscopic constant formula, observed freezing point is 0.0205, which they gave here, but the calculated freezing point, we know that I factor can be calculated by observed freezing point, observed corrugative property by calculated corrugative property. So we will get it around 1.041, which is close to 1. Acetic acid is a weak electrolyte and will dissociate into two ions, acetate and hydrogen, CH3COO minus and H plus, but this is actually very, very less, so it is not reaching 2, it is still close to 1 only. It is not even reaching 1.1. And it dissociates into two ions, acetate and hydrogen per molecule of acetic acid. If X is the degree of dissociation, then you will have N times 1 minus X moles of undissociated acetic acid, N X moles of CH3COO minus, and N X moles of H plus ions. So the total number of moles of particles are N times 1 minus X plus. We will get 1 minus X, 1 plus X, N times 1 plus X. The value for I is 1.041. Actually, we directly got the value instead of this equation. We directly got the I factor. I should be the exact same value we got here as well. So I don't think we need to do this. Degree of dissociation of acetic acid is around 1.041 minus 1, which is 0.041 times 100 if we do, which is 0.4 percentage. Wait, no, 4 percentage of dissociation, not 0.4, it is 4.1 percentage of dissociation. Then they asked, I think, concentration, dissociation constant. They asked for dissociation constant of acid. The Van Hoff factor is 1.041 and degree of dissociation is 4.1%. and we have a formula where degree of dissociation or association, degree of dissociation, no, dissociation constant Ka equals C alpha square. Alpha is the degree of dissociation by 1 minus alpha, where alpha we have here, where the degree of dissociation of acetic acid we have 0.041, which is a small value. We can neglect this. Then concentration C times alpha square, which we will get it to be around Ka, that they have calculated here, which is 1.86 times 10 power minus 5. That is the answer. As for the summary, a solution is a homogeneous mixture of two or more substances. Solutions are classified as solid, liquid, and gaseous solutions. The concentration of solution is expressed in terms of mole fraction, molarity, molality, and in percentages. The dissolution of a gas in a liquid is governed by Henry's law, according to which at a given temperature the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas. The vapor pressure of the solvent is lowered by the pressure of the non-volatile solute in the solution, and this lowering of vapor pressure of the solvent is governed by Raoult's law, according to which the relative lowering of vapor pressure of the solvent over a solution is equal to the mole fraction of a non-volatile solute present in the solution. However, in a binary liquid solution, if both the components of the solutions are volatile, then another form of Raoult's law is used. Mathematically, this form of the Raoult's law is stated as P total equals P1 plus P2, where P1 and P2 values we know from the Raoult's law itself. Solutions which obey Raoult's law over the entire range of concentration are called ideal solutions over the entire range. Two types of deviations or non-ideal solutions from Raoult's law are called positive and negative deviations are observed. Azeotropes arise due to the very large deviation from Raoult's law, and they have similar boiling points, so we cannot separate through fractional distillation. The properties of solutions which depend on the number of solute particles and are independent of their chemical identity are called as colligative properties. These are lowering of the vapor pressure, elevation of boiling point, depression of freezing point, osmotic pressure. The process of osmosis can be reversed if a pressure higher than the osmotic pressure is applied to the solution. Colligative properties have been used to determine the molar mass of solutes. Solutes which dissociate into solution exhibit molar mass lower than the actual molar mass, and those which associate show higher molar mass than their actual values. This is for individual molar mass. Quantitatively, the extent to which a solute is dissociated or associated can be expressed by the Van Hoff factor, that is I. This factor has been defined as ratio of normal molar mass to experimentally determined molar mass, or as the ratio of observed colligative property to the calculated colligative property. With this, we have completed first revision of solutions chapter of chemistry, solutions chapter 1 of chemistry via NCERT completed. See you in the next video.